So welcome to this Thursday morning session. We'll be talking about deoxygenation, water quality, and the climate system, and then with specific attention to processes, feedbacks, and actionable indicators. So my name's Caroline Slump, and I'm co-chairing this session with Nancy Rabelais, but she'll be connecting from a distance today. I'm really happy to announce our first speaker. So it's a great pleasure to announce Jeremy Testa from the University of Maryland, Chesapeake Biological Laboratory, and he'll be talking about dissolved oxygen as a keystone molecule in coastal ecosystems.
That's good. Good morning. Thank you, Caroline, and thank you, Nancy, for inviting me to be here. Thanks for everybody for contributing to what I think has been a really great meeting so far, and thank you for coming after banquet night. It's nice to see you all here. So I decided to take a little bit of change of course to try to narrow down what I'm going to talk about today, and I'm going to kind of focus in on estuarine ecosystems and how they respond to multiple types of anthropogenic forcing, and sort of consider the role of various types of oxygen-induced feedbacks on the cycle. So just to give you a little bit of an idea of what I'm going to try to cover, the scope. So I'm going to reflect a little bit on estuarine hypoxia under multiple anthropogenic stressors briefly, discuss deoxygenation in the context of feedback processes, and I'm going to sort of end the talk with a case study of this system we've been working in where we can do experimental oxygenation of the water column. So I know that in a meeting like this, it seems kind of silly to talk about what would happen in the future in terms of hypoxia, but in the coastal zone, there's multiple factors involved in climate change that can enhance deoxygenation. So, for example, projections of hypoxia in the northern Gulf of Mexico suggest a higher frequency of larger hypoxic zones, and that's largely due to warming, but it's also due to things like elevated river flow. The Salish Sea is a place that doesn't have low oxygen water right now, but projections for the end of the century have a pretty large expansion of water. And that's involved with warming, but it's also associated with effects at its seaward boundary. Now, as we move into estuaries, especially those estuaries that have eutrophication-induced deoxygenation, the potential for, deoxygenation to get worse in the future because of warming, there's at least a knob that can be turned associated with reducing nutrient loads and sort of taking that part out of the picture. And just to give a couple of examples of the few papers that are out that have tried to address this to some extent, this is an example of a paper from Chesapeake Bay, of which there's been 2 recently. And what these papers have done is use modeling analysis to sort of hindcast hypoxia in Chesapeake Bay. And both analyses found that warming that's happened in the contemporary time, just over the past 30 years, has been enough to undo some of the improvements of hypoxia that actually would have been expected from nutrient load reduction. Similarly, in Long Island Sound, this paper by Whitney and Vlahos, they're pointing to a increase in oxygen in the Western Long Island Sound recently, associated with a decrease in nutrient load. But looking ahead in the future, they see some of these improvements with oxygen stabilizing or being even overcome by warming. So there's this interaction between nutrient load and warming. And it's a very real thing for those systems where nutrient loads are being managed to be reduced. Because, for example, the Chesapeake Bay program that's looking to reduce nutrients to Chesapeake Bay, they're working very hard to try to update their nutrient targets to try to make up for this expectation that they're going to need to reduce nutrient loads more to get the oxygen response they originally targeted. So I've used these diagrams in the past to kind of consider the relationship between nutrient loading and hypoxia and try to consider it in different systems that have different types of controlling factors involved. And so these are pretty hypothetical, but they sort of force you to put a hypothesis into play for how we expect different things to mediate this nutrient hypoxia relationship. So for example, all of these have a degradation trajectory associated with increasing loads, and then restoration trajectory, if you want to call it that, as the loads are reduced. And so the simplest one would be, and this is how kind of the management programs sort of think of it, that it degrades in one way and it comes right back down the way it degraded. And really, I think the only place I've seen this happen in the literature is in urban estuaries, where the oxygen depletion is driven by direct inputs of oxygen-consuming materials from wastewater treatment plants. Once you improve the treatment plant, take that away, things come back. Another option is this shifting baseline, which is the example from Chesapeake Bay and Long Island Sound, where you had hypoxia go up with nutrient loading, but it's going to come back higher than it was simply because it's warmed, and it has that effect. And now there's these other pathways here that are maybe less clear on what would cause them, but all of them have some sort of nonlinear behavior in them. And the reason that we were thinking about these types of things was a recognition that as hypoxia increases somewhat, the fact that it stimulates nutrient recycling in many places could potentially lead to positive feedbacks that give you a lot more oxygen for a given nutrient load. And so that's what I'm going to spend some time talking about. Now, there's a bunch of examples of these types of positive feedbacks that are out in the literature. So this is just an example from Niemeyer looking sort of on a global scale for phosphorus. And sort of the basic idea here is that perhaps with warming, you have an expanding OMZ, if we want to pick it up on this track. Less oxygen tends to mobilize phosphorus, especially from sediments, which could eventually be put in a place where it can support more production, therefore more breakdown of organic material and more OMZ. So it's sort of a self-reinforcing process. Those of you who are familiar with the Baltic Sea, similar things have been proposed where oxygen depletion leads to elevated sediment phosphorus release, but also some elevated denitrification leading to excess phosphorus, cyanobacterial blooms, and then they, when they're decomposed, lead to more oxygen. This has been called the vicious cycle, and you can sort of see elements of this emerge just by looking at data where hypoxic areas are pretty highly correlated with a pool of inorganic phosphorus that accumulates in bottom water. So I pulled an example that's kind of old at this point. It was some work that I had done for my PhD, where we were thinking about this kind of quote unquote vicious cycle, but we were thinking about it in terms of nitrogen. And we were thinking about it specifically in Chesapeake Bay. And forgive me, this is a horribly simplified nitrogen cycle, but it's really meant to just illustrate the key processes that are behind this hypothesis and kind of constrained by the information we had at the time. So the basic idea here, and most of you would be familiar with some of this idea, is that, organic matter being produced in the water column sinks, some of it's decomposed in the sediments, and some of that ammonium in this case can go back out into the water column and potentially be recycled. If it's an oxygenated environment, and especially if there's benthic invertebrates that are irrigating the sediments, there's plenty of interfaces with oxygen, there's plenty of nitrification, and it can be denitrified or there can be anammox, and so there's sort of a removal of nitrogen from the system. So to contrast that with sort of, you could call it a hypoxic case, or maybe it necessarily has to be anoxic. All the same processes are at play, but the oxygen's gone. In Chesapeake Bay, oftentimes there's sulfide that accumulates in the sediments and in the water column, which restricts the nitrification, and nitrate becomes limiting for denitrification and has the potential to sort of ramp up this process and create this loop. So the reason that we even came to try to think about this hypothesis is that there was this observation that the amount of hypoxia generated for a given nutrient load, over a multi-decade period had doubled sometime around the mid-80s. And so we were reaching for reasons why this sort of amplification of hypoxia would have happened. And that's one of the hypotheses we were trying to test was, could it be this enhanced recycling of ammonium? And so we tried to put that to test just using long-term monitoring data. So we went into some databases and we sort of looked at distributions of ammonium. This is sort of a north to south gradient in Chesapeake Bay, and depth is the y-axis. And so you can see here that the ammonium concentrations have gone up over time. which they should have because the nutrient loads went up. But there's a big increase in the ammonium that accumulates in the bottom water. And what's more relevant here is this index that we computed, which is to take the accumulated ammonium in the bottom water as a fraction of the load that came in. And it's effectively a recycling index that tells you how much of the loaded nitrogen sort of was maintained in the system. And if you relate that to the amount of bottom water hypoxia in some regions of the bay in the summer, you see a pretty positive relationship, right? So this at least established the fact that there was an amplification of recycling and accumulation of relatively bioavailable nitrogen. And the same thing was true for phosphorus, although I don't show that here. So this was kind of documenting that at least step one of this proposed feedback could have happened. But there's some problems with this. And when I was giving this talk a couple of times in the past, is some of the few times where people have come up to me right after my talk and said, I really think you're wrong, and I'm going to tell you why. And so let's talk about those really quickly. So one of those ideas was that this whole idea that coupled nitrification, denitrification getting shut down in the sediments would allow this limit N loss. But this idea was that, well, all of these processes happening in an oxygen environment, why couldn't they just migrate up to the picnic line and you'd have that same habitat? It's just been displaced in space. And it actually turns out that some later work showed that there's some significant chemoautotrophic carbon fixation that happens in this layer associated with ammonium and sulfide oxidation. So what was the other problem? I think Nancy pointed this out to me that she didn't like. So, you know, one of the key parts of this to work is that you have to get ammonium back up into the water column, the surface waters that are photic, which are pretty shallow in this system. And the idea is that, well, in order to get that ammonium up there, the diffusion's pretty slow. It's really stratified. You might need turbulence to get up there. And so you might get the ammonium up with that turbulence, but you're all going to be mixing oxygen down. So they're going to sort of compensate for each other. And another possibility, which, you know, I have even come to realize is that, you know, Chesapeake Bay as a temperate ecosystem turns over every fall. It gets cold, the waters mix, and the hypoxia kind of resets. So the potential for a feedback like this to really put the system in a different state where it's sort of self-feeding itself can really only happen for a month or two. And so I don't know that I'm fully ready to put this to rest, but maybe it's time. So all of these examples of feedback that I've talked about so far are kind of in these bigger systems, so they're a little more stable. The hypoxia there is a little bit more persistent. And I want to spend the rest of my time talking about places in nearshore estuaries that aren't as persistent. And so we've seen a couple of talks this week that have shown where, you know, we have dialyl cycling hypoxia where oxygen's going from, you know, 300% saturation to zero just in the course of 24 hours. There's other places in the world where deoxygenation only really sets up for a week or so where it's episodic. And that's in contrast to a place like Chesapeake Bay or the Baltic where you have much more persistent low oxygen conditions. And so I think there's some open questions here that maybe we haven't addressed for how long it takes, you know, feedbacks like this to emerge. You know, are they persistent? Can they be transient? And, you know, what's our capability to really understand them? Because there's so many interconnected processes that are a part of these feedback hypotheses that you almost always need numerical models to really be able to connect all the dots mechanistically. So we tried to take an opportunity to kind of look at these kind of nutrient cycling feedback processes on a much shorter time and space scale. And we were able to do that because there's an experiment, or there's a engineered deoxygenation system that's in this tidal, small tidal creek in the Patapsco estuary, which is where the city of Baltimore is in Maryland. And so this is a map of the watershed. It's a highly urban estuary. And Rock Creek is this little tributary sort of sitting here off the south shore. And so this place, Rock Creek, was going basically sulfidic in the 80s. Then a lot of people live right on this creek, and it was really perceived to be a problem among the citizens that live there. They were experiencing deoxygenation right in their backyard because it stunk, there were fish kills, and they even complained that the paint was peeling off. I forgot that this happened, so my apologies. But so the county actually came to their rescue and installed this aeration system. And you know, the system works. It kind of subverted the eutrophication-induced hypoxia by just mixing the water. And so it gave us an opportunity to really turn these systems on and off and kind of watch, hypoxia and anoxia kind of develop in real time. And so this is just an example of, you can get a sense that the system's only about 3 meters deep. And so, typically we could go out there and measure a profile on one day. The county would turn the aerators off in the afternoon, and the next day we'd come out and the oxygen would already be depleted. And you can kind of see these aerators from the air. I've seen them sort of flying into Baltimore, when I'm coming in. So just to give you an example of how this has worked in the past. So this is a contour plot of oxygen here on the y-axis over time. And this is about a month-long period. And so what you're going to see here is oxygen distributions. And my units are all over the place, my apologies. But we're going from 19 milligrams per liter to basically the detection of the instrument that was used. So that's a pretty aerated environment, top to bottom. And then the aerators go off, and what happens? Well, the oxygen sort of goes to zero almost immediately, close to zero. And over the course of the 2 weeks or so that followed, you see sort of a gradual sort of shoaling of the really low oxygen water. It's getting almost to the surface. And the other sort of interesting thing about this is that this is a pretty turbid system, and these stratification systems are just mixing the algae, right? So they're sort of limited by light when they grow. And when you turn them off, the algae bloom, and you can see that there's all these oxygen peaks here that are on diel cycles, and that's this massive bloom of algae, chlorophyll like 100 micrograms per liter. Okay, so we've been studying this place for a few years and bringing in various collaborators to try to measure different parts of the system. And so what I'm going to show you in the next few slides are primarily data from these two systems that are right in the aeration zone at the very upper part of this creek. And then I'm going to show some data. We usually would put an oxygen mooring out on Karen's dock. I guess it's Karen's last name is Canfield. This isn't the Don Canfield dock, but it's the Karen Canfield dock. And we did experiments in 2012, 2016, 2018, and 2019. And they had different timescales of how long they were off. So there was a 1-day experiment, a 7-day experiment, 10 days, and 14 days. And what I'm going to focus on today is the measurements we made of sediment water fluxes of ammonium and N2, oxygen, nitrate, and phosphate. I might get to the methane and nitrous oxide concentrations that we measured, which is we're just sort of getting into now. And there's been a lot of sort of metals work by one of our colleagues too, but we haven't sort of have all that to show quite yet. Okay, there we go. So here's an oxygen time series from our experiment in 2018. And notice we're going from July 9th to July 20th here. And the orange is when the aerators were off and when they were turned back on. And this is the period when the aerators were not on. And so one of the things you'll notice is that oxygen was already pretty low before the aerators were turned on, but that's because this particular mooring is just outside the aerator zone, right? So there's sort of a limit to where these aerators they can be felt. And so every time we did one of these experiments, we saw it as sort of this like neat, nice ecosystem experiment. But there was always some physical change that happened that sort of confounded what we were doing. And in this particular year, a day or two after we turned off the aerators, there's this big injection of oxygen associated with some sort of physical advection that we measured coming in from upstream. But then after about 7 days or so, the oxygen came down to a place where it was pretty much as low as we can measure it. And just to start with the phosphate concentrations we saw, this is just looking over a 10-day period of record. So these are bottom water concentrations at one of the stations in the aeration zone. And you can see the oxygen dipped down, it came back up with that event and eventually came back down to really low levels. And it wasn't until it had been there for a day or two that we saw the phosphate come up. And we found a similar thing at the station right next to it, right? So the phosphorus in the water column responded actually pretty quickly to the deoxygenation, but it sort of had to get there. And we sort of expressed this when we looked over a bunch of the experiments that we did and even the concentrations within one experiment. And so what I'm plotting here is the 7-day increase in the water column phosphate at different stations relative to the consecutive days that they had been in relatively low oxygen conditions. And you can see that, you know, the accumulation happens, you know, on the scale of, you know, 2 to 5 days. At one day, you don't really see an effect. It takes a week or so for this to set up. So what's causing this? So the emergence of these elevated P fluxes can be documented in the sediment water incubations we did. So what you're looking at here are sort of the average sediment water phosphate flux measured in the 2012 experiment, which was 14 days long. And so the fluxes, which are actually really enormous, after being off at 2 days and being nearly sulfitic, and it was basically at zero when they were on, right? So there was this big response to the sediment water phosphate fluxes. In 2018, we really only had 7 days of deoxygenation. You still see this effect, but it's much more muted. And then if we go to 2016, where we only did sort of 1-day experiments, we really don't see sort of a substantial change at all. So it sort of tells us that we can sort of see this phosphorus effect relatively rapidly. It takes a few days, but it's there. And you know, the thing that I didn't really have time to talk about today is what we measured on the nitrogen side. And we didn't really see a strong response to our sort of 1-day, 5-day, 7-day experiments with the nitrogen. And that's consistent with some work that I've recently seen where, you know, it seems like phosphorus is much more responsive than nitrogen. We're at 20? Okay. Okay, so the last couple of slides, and this is data that we haven't really had a great opportunity to really look at in detail, but these are the nitrous oxide concentrations that we measured in our 7-day experiment. So this is 2 stations here within the aeration zone. And so this is the on right here, and then the off is right next to them. And so the first thing is the nitrous oxide here is actually pretty high. It's above saturation. So this Rock Creek is you know, putting nitrous oxide into the atmosphere. Note that the light green bars are the surface and the dark green bars are the bottom. And so during the off phase, you start to see the nitrous oxide come down somewhat, especially at station 2. And it's not, and so you can see that this, you know, if you just compare the on and the off. And so we don't really have the sort of rate measurements or the data at time to sort of say anything conclusive about this, but it just does suggest that, you know, by July 17th in this case, by the time you were here, that nitrous oxide was coming down, probably most likely because the ammonium oxidation had slowed down and there was just less production, but it could also be that it was just being reduced because the oxygen concentrations had come pretty low. So the last slide I want to show from this are the methane concentrations that my colleague Laura Lapham has measured, and this is part of a bigger paper on the methane fluxes that she did. And so what we found is when we did the 1-day experiments, there's almost no difference in methane. You know, the methane's really high. Rock Creek's exporting methane to the atmosphere, but there wasn't really a difference after a day. If you look at a couple of stations in the aeration zone, which are these 2 plots on the bottom, you see methane really accumulating in the bottom water after a much longer experiment. So we don't see that response quickly, but we see it within the course of, you know, 7 days to 2 months. So there's a response here. And, you know, really, there's a lot to be done here. We started collaborating with people that are trying to look at the microbial communities that are active and present here. We don't really have that data yet, but, you know, this is sort of a system we're going to sort of come back to. We've been pretty descriptive up until now, but hopefully we can get a wider variety of rates and address a wider variety of processes in the future. So I'm going to end here and just sort of talk and summarize that the interplay between these diverse drivers of oxygen and how they're going to lead to oxygen outcomes in estuaries, is kind of uncertain. Makes it pretty hard to predict the future because there's, multiple controlling factors involved. Ecosystem feedbacks, they're time and space dependent, and there's an element of, the physical setting and the system specificity of those feedbacks that's worth considering with models. And when we measured the near-term evolution of some of these feedback mechanisms, it kind of gave us this opportunity to quantify their timescales, which we found in this case to be pretty different for N and P. And so as always, there's much more to learn. I think some of the talks coming in this session are going to dig into related ideas with some other data, but I'm going to end there. Thank you for your attention, and I'd be happy to take any questions.
Okay, well, thanks for a great talk and very nice in time, so we have plenty of time. So, Don.
Thanks for a great talk, Jeremy. So back to this sort of doubling of an oxy associated or hypoxia associated with the same nutrient load that you identified in the Chesapeake Bay. Maybe but could some of that be attributed to an accumulated oxygen sink over time from organic matter that's settled down into the bottom into the sediments, and then just over time there's huge oxygen sink that just accumulates there? And then part of your hysteresis again, of course, would be of that organic matter over time, nutrient concentrations were normalized again, or nutrient loads normalized again.
Yeah, I don't think I have, any. Well, what I can say to that is there's some evidence that even under these conditions, that the sediments in Chesapeake Bay actually they kind of slow down reactively, even towards the end of any given growing season. So like, for example, the ammonium fluxes you see from the sediments in August in some years start to go down, even though the temperatures are really high. And one of the reasons for that could be that it's warm and they're sort of burning through that organic matter, even that organic matter in a given year. But that's all the really empirical information I have to address that question. But what's also relevant to it is that probably the more compelling argument that's been published about why this shift happened is that there was a change in the wind direction in the bay associated with sort of larger scale variability. And the change was such that the stratification in the system was higher. And so there was less sort of physical replenishment of the oxygen. So it may not be something by geochemical at all. It may just be simply something that's physical. And so, yeah.
Hi, it was a very nice presentation. I just was curious about something. In one of your figures, you put the bioturbation with oxygen, but with low oxygen, the bioturbation is gone. It's because just they dead, or they have no role in the oxygenation in the sediment, and is a phosphorus limited environment, because you didn't tell, so I don't know if you was or no. I'm just curious about this.
So in terms of the benthic organisms, I think the idea in this particular system is that in the summer, the sediments in the main part of that are hypoxic are pretty much have no benthic organisms in them. And if you look at some of the long-term benthic data, there were bigger, longer-lived species like Macoma that sort of started disappearing around the time, actually, the mid-'80s, when you started getting more hypoxia per load. So that's kind of like an element of that we have a little bit of information on. The second question is, this is more, the bigger parts of Chesapeake Bay, seaward parts, are probably more N-limited than P-limited, but there is P-limitation, we think, in sort of the more northern part of the bay and in kind of the winter-spring time period. So there is a role for phosphorus to have an impact on the phytoplankton production. It's just smaller than nitrogen, we think.
Okay, there's time for one more question. I think
Hi, thanks for a nice talk. So in eutrophic lakes, there are a lot of these, and in many cases, they've been proven on the longer term to be quite ineffective for improving the water quality in terms of frequency of blooms or the surface water phosphate concentrations. And it's often because, as well as, of course, mixing down the oxygen, you also increase the temperature of the bottom waters. So you accelerate the rate of remineralization, and effectively you bring the nutrients back into the cycle this way. So in this case study, is it an effective method? In fact, you've shown it's quite an effective method for reoxygenating the deep waters, but is it actually improving on the long term the water quality in this system? And if so, why?
Yeah, that's a great question. I think I don't think I really have the information to answer it sufficiently. You know, and I guess it depends on what your target is. You know, it's successful at bringing oxygen to a certain part of the estuary. And although I sort of said something that might disagree with this statement, when we've turned the aerators back on, you actually see a little bit of an expansion of the oxygenated zone outside of the aerators. So it does actually have an oxygenation effect outside of its physical footprint. We don't have enough long-term data, I think, to really know if it's doing anything to improve it in the long term. I haven't seen like a reduction in the percent carbon or nitrogen or phosphorus that's in the sediment, even over the course of these years that we've studied it. And there's still really high concentrations of chlorophyll there and blooms happening. So I think you're right that it's not really solving the overall water quality problem in this creek. It's just kind of putting a Band-Aid on the oxygen problem. And I guess if you think that's good enough, the people that live there love this system. And whenever we turn it off, they're out there asking us what's going on. They're really concerned about it. I mean, so that's what I have. Thank you.
okay, well, thanks again. Thanks for a great talk, Ben. And we're going to move on to the next talk by Noor Boukour from the University of Angers. We'll be talking about oxygen deficits in macrotidal estuaries, the role of benthic geochemical fluxes.
Is this fine? Yeah, okay. Oh, I can't see it here. Okay. So good morning, everyone. I'm very glad to be here today to talk to you about the dynamics of geochemical fluxes in a hypoxic, in a seasonally hypoxic estuary. So I want you to know that these the project started not long ago. So these are preliminary results that need to be further processed. So without further ado, let's get into it. So here is again that figure that keeps coming. So I'm pretty sure that if we're all here, we are all aware that our waters are suffocating all around the world. And if some of you had a doubt, I think with the past presentations, we all became sure of that. So I'm not going to go over what already have been said. What I need to highlight here is that the oxygen variations are mainly governed by interactions with physical and biogeochemical processes. But also, I want to highlight the impacts we see in coastal areas and most precisely in estuaries. So alongside the modification of biogeochemical cycles, in estuaries we observe the migratory fish species having trouble to migrate due to the lack of oxygen, but they also see an increase in their sensitivity to contaminants. So together we're going to explore the Loire estuary, which is located on the west coast of France. The Loire River is a river that counts a watershed which is highly anthropized, with a surface area of more than 100,000 square kilometers. Its estuarine zone counts a surface area of 60 square kilometers. It's a turbid and a macrotidal estuary. So the tide range is about 4 meters at the mouth, and the tidal wave can go and propagate up to 97 kilometers. So as I said, not only it is a microtidal, but it is also turbid. So the SPM, or the suspended particulate matter concentration, can go higher than 0.5 gram per liters in the turbid or the maximum turbidity zone. Here we can see the extension of the maximum turbidity zone. It goes up to, it extends on 40 kilometers. Its location and extension depends on it is mainly governed by the tidal coefficient, but the river flow. This TMZ, as we can see here, is negatively correlated to the SPM, sorry, is negatively correlated to the oxygenation. And so we quantify this, we qualify, sorry, this TMZ to be a home to these hypoxias. So the oxygen also varies with other parameters, notably the tidal cycle. Here we observe 3 measurements made in surface and mid-depth of salinity and oxygen from the upstream to the downstream stations. And these measurements show a good correlation between the salinity and oxygen. So in the upstream station, we see there on the left where the salinity intrusion is nowhere to be found. The oxygen don't variate very little, but also it stays pretty high. In the midstream estuary, what we see in the middle, we see a negative correlation between the salinity and the oxygen, to switch to a positive one in the downstream stations. So not only it is influenced by the tidal, the oxygen distribution is also influenced by the river discharge. We see these deficits globally. We see these deficits in oxygen during low water flow, especially when we get to a flow inferior to 500 cubic meter per second. And so it is correlated to the flow, but also the tide, and so the salinity. So in the past 30 years, although the nutrient loads from the river got better due to the water quality management and policies, we still observe those hypoxias in the Loire. And one of the impacts, as I said before, is that it disturbs the biogeochemical cycles, notably through making the redox fronts go upward towards the interface, and so it generates a positive feedbacks of nutrients to the water column. And so in this project, what we're trying to explore, or our hypothesis, is that the role of the sediment through nutrient loads into the water column in the aggravation and or the apparition of those hypoxias. And so for that, I want to also say that we're trying to do this through exploring the sediment response to those deoxygenation conditions, but also to evaluate the nutrient flux. And that's the part I'm going to show you today. So for that, we carried out 2 campaigns. The first one during February of 2021, during a flood, where the maximum discharge was higher than 4,000 cubic meters per second, and during which we observed erosion of the sediment in the upstream stations, but also methane gas emanations. The second campaign took place in August of the same year, during a low river flow, where the minimum discharge was around 200 cubic meters per second. Here on the map, we can see all the stations we sampled, but also the TMZ, or the maximum turbidity zone, extension and location during each campaign. Keep in mind that the color code is going to be used in the following slides. So, to characterize the water column, we did the profiles of the shown parameters, and to estimate the diffusive fluxes, we used a modelization using the profile package, and for that, we used the nitrate and the ammonium pore water, but also profiles of the oxygen in the sediment. To estimate the total flux, which is the sum of diffusive one and advective one, we put in place incubation experiments. So, without further ado, let's get into the results. So here we can see the 2 upstream stations. We can see the profiles of the water column during flood and low flow. In green, you have the dissolved oxygen. In brown, you have the SPM concentration. In pink, we have temperature, and in blue, we have the salinity. Globally, we have no stratification upstream, regardless of the campaigns. We don't attain the hypoxia threshold, which is of 2 milligrams per liter. We stay oxygenate, mainly goodly oxygenated in all the stations. In station 3, during low flow, we observe a diminution of oxygen between surface and bottom, and that correlates with an increase of SPM during in the bottom. In the downstream stations, so during flood, we observe a stratification that could explain the slight diminution in oxygen from surface to the bottom. So now I'm going to take you into the sediment. So here we can, down here, we can observe the oxygen profiles with the diffusive oxygen flux alongside the depth of penetration of oxygen in the sediment that defines the oxic zone. Here on top, we can see both the diffusive and total oxygen uptake, but only during the flood campaign. So both these fluxes, so total and diffusive, have a decreasing trend from upstream to downstream, and while the depth of penetration is increasing from upstream to downstream, and that is related to the oxygen demand, which is higher at the upstream stations, and we link that to the emergence of anoxic sediment when we erode when we eroded the sediment. And so we proceeded then to compare the diffusive and total oxygen uptake. As we can see here, in the downstream stations, or at least the last one, the station 6, the diffusive fluxes are mainly the main contributor in the flux or the oxygen uptake. However, in the upstream stations, we see that the ratio between total and diffusive one is that of 3. And so that emphasizes the importance of advective processes in the upstream. And we associate that as a result with the methane emanation and the mud cracking we observed, as you can see in the pictures. So now I'm going to talk about nitrate. Here we can see the nitrate profiles during both campaigns, so with the same code color. And up there we can see the diffusive flux of nitrate. During flood, we observe an increasing trend along the salinity gradient. However, during low river flow, we have no flux of nitrate in the downstream station, and we associate that to the salinity, which was that of 30. Here we have a nitrate flux going to the sediment, to the water column, sorry, and that is probably due to this nitrification peak we see here that needs to be explained with further analysis of the pore water chemistry. As for ammonium, during flood, which is the bars showed in red, so we have a decreasing trend between station 1, 3, and 6. However, station 5 showed a distinct behavior, which could be due to the TMZ presence there, but still we haven't seen that the station 6 go out of the trend. So it's something to explore furthermore. During low flow, we see no trend, and again the station 5 shows a distinct behavior during the 2 campaigns. So unfortunately, I have to stop here. I want to recap on. I want to do a recap on what I said. So we got familiar with the Loire estuary, that it's macrotidal, that it's turbid. It has a seasonal hypoxias, which is positively correlated to the maximum turbidity zone, but also the river discharge. We saw that the river flow had a negative impact on the sediment as it eroded it, which caused methane emanation, higher the oxygen the demand. But it also made the advective processes go more important. So as a perspectives of my project, we need to link the observed pore waters to the other pore water chemistry, because we don't just analyze what I showed you, but we do extraction experiments. We do trace metals analysis, and so much other things. There's a need to estimate the total oxygen uptake for the other campaigns, but also the total fluxes for the other elements, and we need also to investigate the phosphorus dynamics, and also characterize the organic matter in order to explain what we're seeing, and there's obviously something happening, and we hope that we can tell a beautiful story at the end of this. So thank you for your attention, and I welcome any questions.
Okay,
Thank you very much. So given the time, we need to move on to the next talk. So I hope there's some time for discussion at the end. So the next speaker is Olga Sigodlowska from Utrecht University. She'll be talking about methane removal in the sediment and water column of a seasonally hypoxic eutrophic marine basin.
Hello, good morning, everyone. Very happy to be here today. So I will be talking about my work on methane removal in sediment and water column in coastal zones today. So as we all know, methane is an important greenhouse gas and its concentrations have been increasing in the atmosphere in the past century. We have processes like rising temperature, eutrophication, and ocean deoxygenation that leads to increased production of organic matter, but also increased anaerobic degradation of organic matter in the sediments. And that leads to increased production of methane and release of nutrients, which then can have an impact on the rising temperature, eutrophication, and ocean deoxygenation. But most of this methane is removed before it can reach the atmosphere. So how is it removed? So starting from the beginning, we have methane production in the sediments via a process called methanogenesis. And in the anoxic part, it can be removed with sulfate in a so-called sulfate methane transitional zone. And in the oxic environment, methane is removed with oxygen via a process called aerobic oxidation of methane. But we also know that there are also other anaerobic processes that can remove methane. For example, methane can be removed with nitrate, manganese oxides, and iron oxides. And this figure suggests that those processes happen in the sediments. However, when we have anoxic bottom waters, this redox zone can move from the sediments into the water column. And then those alternative processes, anaerobic processes, can also occur in the water column. So who is responsible for those processes? So for the aerobic oxidation of methane, we know, for example, about metallomonas, and they have been found at the edges of oxygen minimum zones. But for the anaerobic methane oxidation, we know about metallominaries, and they have been found to be capable of oxidizing methane coupled to reduction of nitrite. But we also know about metanoperidans, and they have been found to oxidize methane anaerobically coupled to nitrate, and also coupled to manganese and iron oxides, but only in fresh water so far. So in this study, we want to focus on the coastal zones and investigate the potential pathways of aerobic and those alternative anaerobic methane removal pathways in coastal waters. And today I will be focusing on assessing the changes in methane dynamics between season when the water column is fully oxygenated, in our case, early spring, and the season when the water column is stratified, so late summer. So for our sampling site, we went to Lake Revelingen, which is seasonally anoxic marine lake located in the west of the Netherlands. And we focused on the Scharendijke basin, which is the deepest basin in this lake. And this basin is characterized by high salinity, the salinity that is close to the salinity of the North Sea. But we see that the salinity doesn't drive the stratification. It's temperature that drives the stratification. So we see that when the surface temperature increases, and we have this density differences, then that leads to separation of the water masses, so they cannot mix anymore. And the bottom waters become depleted in oxygen very quickly. And then once the temperature becomes constant through the water column at the end of summer, then the water column mixes and becomes oxic again. But the seasonal stratification is not the only reason why we find this place very fascinating. It's also because we know from previous studies that there is a high organic matter input and also high fluxes of methane from the sediment into the water column. So if we start with the water profiles, depth profiles, first thing we see is that we have a huge loss of methane, which is due to the gassing. And the more methane you have, the more methane you lose. It's really difficult to, I'm sorry, someone is calling. The phone, not mine, sorry. Yes, so you lose a lot of methane, and unfortunately we have concentrations of ammonium as well. So we can, based on that, we can because ammonium is also a product of organic matter degradation, same as methane. So we can use this reactive transport model to estimate the concentrations of methane that should be there. And if we do that, we see that there is actually way more methane than we measure, and that it's also quite similar between March and September. It's basically the same. So now that we have a proper profile for methane, you can see that when the methane is decreasing upwards, the sulfate is decreasing downwards. I'm just going to turn it off. It's starting. Yes, so that suggests that there is oxidation of methane with sulfate. So to further investigate this, we can look at the methane isotopes. So that can tell us where this oxidation is located and how strong it is. So to quickly explain, when we see enrichment in delta 13C and delta D, that means that there is more of the heavier carbon and hydrogen, which means that the lighter one was taken up by the microorganisms. So that suggests oxidation of methane. And we don't really see much enrichment in September, and we see a little bit more in March, but not so much, except for this one point at the very surface. And that is due to the presence of oxygen. So if we zoom in into the first 5 centimeters of the sediments, we see that oxygen is penetrating into the sediments. So that is giving this strong signal in the isotopes, this oxidation signal. But despite this presence of oxygen, we see that methane is actually escaping from the sediments in both March and September. And March is escaping at the rate of 0.1 millimole per meter square per day. And then September is twice as much. So while in March, when this methane escapes into the water column, it can be oxidized with oxygen as the waters are oxygenated. In September, when the water column is stratified, we see that, and this is temperature-induced stratification, we see that methane and ammonium are both escaping from the sediments into the water column, and they are both removed near the oxyc line. So again, we can have a look at the isotopes, so delta 13C and delta D. And here we see the strong enrichment above the oxyc line, near the oxyc line, which suggests that this is where the methane is removed. And we can say that it's mostly removed of oxygen because that's also where this oxygen is already present. But if we look at ammonium, we see that the oxidation of ammonium, removal of ammonium is also at the oxyc line, but we don't see much accumulation of nitrate. So we think that it must be removed immediately. And the question is via which pathways, and could it be linked to methane? So to try to investigate that further, we look at the 16S RNA sequencing data. And we find metylomonas in the bacteria family. So those are the ones that can oxidize methane aerobically, but they are also capable of the nitrification. So they're located here, the red ones near the oxyc line. The oxyc line is the dashed line. But we also, which is much more interesting, we also find those metalloperidans, and they can be found also near the oxyc line is the yellow one. And those are the anaerobic methane oxidizers that are capable of nitrate-dependent anaerobic oxidation of methane. But despite all of those oxidation processes, we still see that the concentrations of methane in the surface waters are actually higher than the concentrations of the average concentrations of methane in the atmosphere. And that suggests that we have a diffusive flux from the water column into the atmosphere. And in addition to that, we also, while being on the ship, we also see a lot of bubbles coming out of the water. So that also suggests that there is a lot of ebullition, and this ebullition strongly contributes to the release of methane from the water column into the atmosphere. So to conclude everything, we have this insufficient removal of methane in the sediments, and that leads to release of methane from the sediments into the water column in both oxygenated period and anoxic period. And then while in the oxic period, methane can be removed in the bottom waters with oxygen. In the anoxic period in September, methane is removed at the oxyc line via aerobic processes, oxidation pathways, but also possibly anaerobic oxidation pathways. but those pathways are not efficient enough, and there is a likely flux of methane from the water column into the atmosphere. And to quickly come back to this first picture, we see that the seasonally hypoxic coastal systems, they can have this insufficient removal of methane, and that can then result in this positive feedback. So low oxygen systems can have this positive feedback and can contribute to release of methane into the atmosphere. So to leave you that sad message, thank you very much, and yeah, thanks.
Okay, thank you. We have time for a question. Yeah. Lisa?
Very nice talk. Is there any carbonate precipitation associated with the anaerobic oxidation of methane that's going on in the sediments?
I don't know about this. I know that in our sediments, we don't see anything. It's literally like this black mud that there is nothing there. So yeah.
Yeah, I mean, it happens in the ocean. So I'm just curious about why there might not be. I don't know.
Yes.
Maybe somebody else here knows.
Maybe one more question. So, Don?
Yeah, thanks for a great talk. Just real quick, did you happen to measure the methane content of the bubbles, what you're ebulating into the water column and then out into the atmosphere?
If we measure the bubbles.
Yeah, the methane content of the bubbles that are coming out from the sediment and migrating through the water column, sort of up towards the top of the water column.
Yes, we tried to do that last year, but unfortunately it failed. Well, we will be trying again next fieldworks. And we also have those floating chambers that can measure the flux of methane. So that's also what we have been doing last year. So it's not included here yet, but that's also something we are working on currently to quantify that. Yeah.
Okay, well, thank you again.
Thank you.
We need to move on to the next speaker. Next speaker is Christopher Soames from GEOMAR, and he will be talking about anthropogenic controls on marine nitrogen and iron biogeochemical feedbacks and their contribution to expanding oxygen minimum zones.
Okay, is this? Yeah, that's better. All right, thanks. Yeah, thanks to organizers. It's great to be here. And so we'll kind of be switching a little bit to the larger scale now. And so what I'll be presenting is potential missing biogeochemical feedback that could be, a piece of the puzzle to explain why what we've heard today is that these global biogeochemical models are not reproducing the deoxygenation trend we're seeing in the observations. All right, so this is a little different look. So this is the deoxygenation that's focused on the upper 1200 meters. All right, and so, yeah, I mean, luckily at this stage of the conference, most of my introduction has already been said, but I do want to point out, like, we have this oxygen contour of about 20 micromoles in this black solid line, right? And we can see this is where most of the deoxygenation, the strongest deoxygenation is occurring, just outside these low oxygen zones. And if we further just quickly look at the oxygen change in the different basins, I just want to quickly point out the three basins with the highest rates of deoxygenation are the North Pacific, Equatorial Pacific, and Southern Ocean. And these, of course, are these well-known iron-limited HNLC regions, right? So when I kind of saw this picture, I kind of immediately thought that maybe something is going on with the iron cycle on the biogeochemical side that could be contributing to this deoxygenation trend. Okay, yeah, and so, and just, okay, let's quickly think about the mechanisms, right? I mean, these have already been mentioned, right? But we know as the world is warming, right, this is decreasing sea surface solubility and ventilation. So this is kind of a physical mechanism which can result in an expansion of OMZs. But on the other hand, stratification tends to reduce the nutrient-rich upwelling, which can, on the other hand, reduce productivity, which respires oxygen, and then this can then decrease the OMZs, right? So we already have a couple counteracting effects, and this is kind of what's been said. It's then difficult to predict, what's even going to be the sign of change of the OMZs due to warming, right? But I'm going to focus more on these biogeochemical feedbacks today, right? And so we are increasing the amount of pollutants, of limiting nutrients into the surface ocean, which can fertilize productivity and increase respiration in these OMZs, right? And we know iron is this redox sensitive element that's reduced to a more bioavailable form of this iron 2, right? And so if this flux increases and this iron can make it to the surface, this could further increase productivity, which kind of can be this positive feedback, right? But we have to remember in these OMZs, that nitrogen is reduced to dinitrogen gas, which is not bioavailable for most phytoplankton species. So this represents a negative feedback that would then reduce productivity that you kind of have to break for a positive feedback to develop. But nitrogen fixation, which is one of the main sources of nitrogen into the ocean, one of its main limiting nutrients is iron, right? So kind of the spoiler alert of what I'll be showing later with my model, that if I include all of these processes, right, and the iron can stimulate extra nitrogen fixation, this can kind of break this nitrogen cycle and result in an expanded oxygen minimum zone. All right, so just let's quickly look at the model structure. So it's intersystem climate model of intermediate complexity, it's relative coarse resolution, and we have a simplified atmosphere where we just force winds. And so then if we look at the biogeochemical side, we have one regular phytoplankton that takes up the nutrients nitrate, phosphate, and dissolved iron at a constant Redfield stoichiometry. We have one class of nitrogen fixing diazotrophs, which are then only limited by phosphate and iron, right? And we also include these nitrogen loss terms in the denitrification in the OMZ and in the sediments. And we also have this iron release, right? And so the sediment fluxes are mainly driven by the amount of POC exporting into the sediments. And then I'll also show a parameterization where, for example, the iron release is also enhanced under low bottom water oxygen conditions. All right, and iron is also scavenged out quite rapidly in some instances. And then I'll be showing some scenarios with increasing atmospheric nitrogen and iron deposition. All right, and of course we have the full set of interactions. All right, so I'll be showing 5 model experiments. One is kind of this control experiment where I essentially deactivate all of these biogeochemical processes that can contribute to this positive feedback. All right, so I'll be showing an experiment I call iron, which I just include this bottom water oxygen dependency. So this will release a lot more iron from the sediments, basically in the OMZs. All right, so this nitrogen simulation will include nitrogen fixation and denitrification alone. And then I'll have this iron plus nitrogen where I activate kind of all of these internal biogeochemical feedbacks. And then I'll include one more where I then include scenarios of increasing atmospheric deposition from pollutants of iron and nitrogen. All right, so we'll be looking at these transient scenarios kind of from pre-industrial to year 2100, right? And so I'll just be showing a business as usual forced atmospheric CO2. And what's more unique is I'll be showing kind of these increasing scenarios of atmospheric nitrogen and iron deposition. So these are from completely independent atmospheric chemistry models. So the atmospheric nitrogen deposition increases by a factor of a little over 2, but nitrogen fixation is actually a much larger source, right? So if we kind of weight the total increase for atmospheric nitrogen deposition plus nitrogen fixation, it represents about an 18% increase in this flux to the surface. Right, and this iron scenario, their best estimate was about a 24% increase. And these were mostly driven by fossil fuel emissions, but the iron also had also an important impact from biomass burning and wildfires. And so, so I mean, these are very idealized scenarios, which are really designed so we can sort out the biogeochemical feedbacks, right? And so, for example, I haven't changed winds at all in these scenarios. All right, so let's look at some results now. Right, and so on the y-axis, I'll be showing the change relative to pre-industrial, and I'm going to be zooming in on this area from 1900 to 2050. Right, and so this top panel is the change in net primary production, NPP. Right, and we can see in this control experiment, we see this big decrease. Right, and so focusing on the tropical ocean, this is what a lot of these global biogeochemical models do, is this reduced upwelling of nutrient-rich waters results in less productivity and less NPP, right? And of course, the oxygen minimum zones are affected by this. And so in this scenario, we also see a decrease in OMCs, which of course we don't see in the observations. Right, and so let's look at this iron-only scenario. And again, we can see very little change when I include this, this bottom water oxygen dependency on the sedimentary iron release. All right, and so in our nitrogen-only experiment, we can see the decrease isn't as much. And I'll kind of show that in the next slide. That's because nitrogen fixation can kind of sustain a little more productivity here. And so now there's just a slight decrease in the oxygen minimum zone. But the interesting thing is now when I include all of these biogeochemical feedbacks together, we can actually see the sign of the change of the model is different, right? Is now we're seeing an increase in NPP, and the OMZs are also following suit. And as you can probably imagine, I continue to fertilize the ocean with more nitrogen and iron going into the surface. Now I can see an even greater increase in the PP, and the oxygen minimum zones are even more sensitive to that. Right, and so including all these biogeochemical feedbacks kind of fundamentally altered the response and the sign of the change of the response in the tropical ocean and the OMZs. And so let's look at a couple of these key processes that I mentioned that could be driving this result. All right, so here on the top again, we have a kind of similar structure here, but here we're looking at the sedimentary iron release and changes in nitrogen fixation, right? And so this control experiment, I mean, it does have sedimentary iron release, but it essentially is following productivity because it's driven by the POC export into the sediments, right? And so that's also decreasing. And kind of the first interesting thing is here is in the iron scenario, right? I mean, this also had decreasing NPP and decreasing OMZs. So actually the positive feedback kind of worked in the wrong direction, right? So it actually decreased a little bit in this scenario because there was nothing to really kickstart NPP enough to really induce this positive feedback, right? And these scenarios don't have nitrogen fixation included at all. All right, so we can see in the nitrogen experiment that, you know, a slight increase in nitrogen fixation was able to sustain a little more of that NPP, right? And so we don't see as much of a decrease. We see a very minor decrease in the sedimentary iron release. But again, when we include everything together, we see this much stronger response, right? So this extra NPP, and they kind of act in concert, right? So we have more sedimentary iron release, which can fuel higher nitrogen fixation, right? And then that's also going to increase the NPP of the system, which continue to fuel additional sedimentary iron release, right? So that's kind of this positive feedback we can see developing here. Right, and so then when we continue to fertilize the ocean with increasing atmospheric nitrogen and iron, again, we can see even higher rates of sedimentary iron release, but nitrogen fixation wasn't as sensitive, and that's because we're adding both iron and nitrogen. Right, and nitrogen also reduces nitrogen limitation, right? And so that kind of reduces the ecological niche for these nitrogen fixers. So there's kind of this counteracting effect from increasing iron deposition, which was stimulating extra nitrogen fixation, whereas the increased nitrogen deposition was kind of decreases nitrogen fixation there, but it's still resulting in a lot more productivity. All right, so that's what we can see here. On top of these extra nutrients I'm adding due to these pollutant scenarios, we can see that kind of the internal biogeochemical feedbacks are now also introducing a lot more iron and nitrogen into the system, which can then really produce higher NPP and really drive these OMZ patterns. All right, so then now let's kind of compare it to this, this deoxygenation figures that we've shown that are based on the observations, right? And so we can see here, so this is this control experiment, right? And it's a little difficult to see with these shades, but we can see kind of this light blue shade, which I showed earlier, which this control experiment simulates a reduction in the OMZs, right? So higher oxygen, right? So then when we control this scenario with all the biogeochemical feedbacks, we can see this kind of light blue is shifting into the light red. And so then it's easier to see if we look at the difference and also zoom in on the scale, we can actually see now where these biogeochemical feedbacks are driving deoxygenation in the model, right? And we can see spatially, they actually match up pretty well with where the highest rates of deoxygenation are occurring in kind of this interpolated data product. Right, I mean, so I should mention I'm still underestimating this deoxygenation trend, especially in this tropical ocean. But at least, of course, I'm not really discussing the uncertainties here, but I think the fact that spatially it corresponds quite well kind of suggests that this could be a mechanism that we should consider in models that could help reproduce the deoxygenation trend. All right, yeah, so I'll just kind of sum up now. And so I've kind of identified a potential key missing link in global biogeochemical models that could help us reproduce this deoxygenation trend. And, I really want to emphasize that, some groups are really focused only on the nitrogen, some will focus only on the iron. And it's like, unless you include all of these together, right, this is what I needed to do in my model to actually start to reproduce this deoxygenation trend. And one kind of final point here, we hear a lot about nitrogen and phosphorus, and those will be most important, pollutants for coastal systems. But for thinking about the more global deoxygenation, and especially expanding to more this open ocean deoxygenation patterns, we're seeing iron was just as important, if not even more important in some regions. So I think I know that's a more difficult thing to measure, but I think we should try to start considering that more when we can. And so I'll end there and take any questions.
Okay, thanks. We have time for 2 questions.
Thank you. Very interesting. I was wondering though, because a lot of the models, the Earth system models, do include those processes you're talking about. Maybe they don't include them in a perfect way, but a lot of those processes are already in our suites of models. So how do you, reconcile what you're saying that we're missing those processes, but actually we do have some of those in our system models that predict those apparently contradicting
right,
trends.
and it's hard to generalize, right, because there are a lot of different IPCC type models, right, but not many include the bottom water, a really intense bottom water effect on sedimentary iron release. Most of them, is driven by the carbon flux into the sediments. Right, and some of them have one important point is some of them do have a low oxygen threshold, where essentially if you get like really anoxic, they release some more iron. But what is different about this parameterization is it starts to release more iron already at around 60 micromoles bottom water oxygen, right? Because that's when they start to see enhanced fluxes of iron. And then as you continue to go, so I do have this plot actually, right? And so, yeah, so this doesn't show it perfectly, but yeah, so what we can see here is the red and the orange are trending to lower oxygen. Yeah, and so I didn't have the second part of this panel, which would have been better, but yeah, so here's what we can see is that, most models just make it a function of the carbon oxidation rate. And so kind of this black line here, but we can see within the variability within this black line, when oxygen is lower, which is in this red and orange values, we see higher irons. But yeah, I'm happy to.
Okay, one quick question.
Hi, thank you for your talk. I was wondering if you could speculate about the discrepancies, either for the mechanism driving the changes or the discrepancies between your model and what we see in the Southern Ocean and then, in the Eastern Equatorial Pacific.
So, oops, this is. Right, yeah, so, in general, right, what we see is just the deoxygenation is too low, right? The high latitude response and that's the thing the models agree on the most, is this more solubility driven high latitude response. but you said the Eastern Equatorial Pacific, right? And yeah, so again, we can see this band is still not there, right? And one potential mechanism is also ventilation, right? So if ventilation is decreasing more in my model, which I mean, there's this recent paper, which I think Pierce Buchanan will probably talk about tomorrow, right? If there is a physical mechanism contributing to deoxygenation, right? There could be kind of this double whammy effect, is the direct effect, and then these biogeochemical fluxes could also be enhanced. And so it's, yeah, I mean, I guess that's.
Okay, well, thanks again. So I'm happy to announce our next speaker, Cleosa Trevisan from the Federal Fluminense University in Brazil, and she will talk about phosphate fluxes between the water column phosphate fluxes between water column and anoxic sediments from a tropical hypersaline lagoon.
Okay. Good morning. It's an honor to be here and share it with you. My name is Cleosa, and together with my colleagues, we present a small part of my thesis about phosphate fluxes in anoxic sediments from a tropical hypersaline lagoon. These are the topics that I will talk about in this presentation, and here are some pictures from my study area. Well, we are in the beginning of the 9 Nations Decade of Ocean Science for Sustainable Development, and coastal zones are considered sink for the continents. They are land sea interface, and their features are under pressure of climate change, pollution, invasive species, and harmful algal blooms. But I'm sure you all know about it, because we have seen this all this week. The general objective of my thesis is to identify the role of anoxic sediments on phosphorus fluxes for distinct water column conditions in the hypersaline Araruama Lagoon. But for this presentation, our objective is to show the different behaviors of phosphate and oxygen reduction potential in water column and sediments for 2 distinct transparency episodes. Araruama Lagoon is in an arid climate region in the state of Rio de Janeiro. Its hydrodynamic is wave-driven due to stronger winds that blow all year, and the internal ellipsoids don't promote a very good exchange of water. It's a phosphorus-limited environment, and the main composition of phosphorus is autogenic. It presents high concentration of carbonates in sediment, and the salinity ranges from 33 to 67 practical salinity unit. The watershed area is 320 square kilometers, but the water body itself is 210. And like many other coastal lagoons, urbanization, high nutrient loads, and another anthropic activities have led to an environmental imbalance and eutrophication process. I will show us a brief historic about the environmental problems in the lagoon. Before 2000, the main composition of the lagoon was benthic microalgae, but in 2005, there was a sudden shift in this community from benthic to phytoplanktonic due to high primary production in water column. And after that, the water that was clear was turned to a brownish color. And then harmful algal blooms, fish mortality, and since 2011, the more frequent presence of toxic phytoplankton and also enterococcus. So, as I said, all these problems were caused by eutrophication due to anthropic activities. Our collections were made in 11 points. The point 1 is outside the lagoon, is a control point of seawater. We have collect water and sediment, and phytoplankton collection is made by an external researcher. And here, these are two pictures from the same place in these different conditions. In March for turbid water, and June for clear water, that the results will be referent to these two campaigns. Our sampling was made in water, in surface and bottom, and we have filtered the water in situ. So we got the particulate and solved fractions. And in sediment, we have collect samples up to 10 centimeters depth. And in laboratory, we got the pore water fraction. We have made many analyses, some of them in situ, and I will present the results for transparency depth and oxygen reduction potential. And in laboratory, among many other analyses, I will show the results for phosphate in dissolved and pore water fraction, and we use the spectrophotometry methodology. Our first result is the transparency, and we can note the difference between these two campaigns, the clear water and turbid water. Here is a bathymetric map, and the lighter areas are deeper than the darker ones, and we understand that the depth is a very important factor for the phosphate fluxes. And here, the results for oxygen reduction potential. We know that in turbid water, the concentration in water column, the values of oxygen reduction potential in water column, they are smaller than in clear water. But the sediments don't exhibit a very different values, and they are in very reducing conditions. In the case of phosphate, here I'll show just the values for water column, because they are so small that we barely see them with the pore water. So the turbid water shows a higher concentration of phosphate in water column than clear water. But the results for pore water, they are almost the opposite, because the values in pore water for turbid water, the turbid campaign, they were smaller, generally smaller than the clear water, but it's not similar. They don't exhibit similar behavior among the points in each campaign, because some of them are higher or smaller between the campaigns. And here, there is a cellular density graph of the phytoplankton, but I just tell you that these campaigns weren't in the same time that our collections of water and sediment, because they aren't made by ourselves. So there are 10 days after our campaigns, but we see the high cellular density in turbid water, and a smaller cellular density in clear water. So we suppose that the turbid water is the primary production is sustained by the high phytoplankton, high phosphate content in sediment, but in clear water, it's smaller, we have smaller values, but maybe some of the points, like this three, that they are higher than in turbid water, maybe could be enhanced or improved the values by the dissolved inorganic nitrogen, because in the water column, the values of phosphate are too small. And here, the toxic species that were found in these two campaigns. So after that, I can tell you that is a conclusion, because it's a very small part of my thesis, and as I showed before, we have many other analyses to study more, but as some propositions for phosphate fluxes and anoxic sediments, we have that for turbid water, it's a positive fluxes from sediment to water column of phosphate. And in the case of clear water, we aren't sure about the negative fluxes that we expect the first time that we collect the water when the water was clear. So because the values are different between among the points in the clear water in sediment. And we also can confirm if there is a cyclic behavior, not only because I show you 2 campaigns here, but we haven't finished our statistical analysis. So after the 8 campaigns that we have done already, after this, the statistical analysis, we can maybe have some questions, some answers. Questions, I already have a lot of them. And about the sediment, we know and we understand the importance of the anoxic sediments because they have a high concentration of phosphate, and then they could be trapped, and they are the traps for phosphate, but the variation in oxygen reduction potential could release this phosphate to water column, and so the sediment would be a source of phosphate from sediment to water column. But we have to understand too the role of pH, the variation in water column and in sediment, the phytoplankton composition, the nitrogen content, depth, and winds, because maybe in the case of depth, the deeper regions could be have a distinct behavior of the shallower areas. The winds that blow all year and maybe could promote any change in the bottom, and also the extracellular polymeric substances and zooplankton. But these 2 parameters we didn't analyze in my research. These are the references that I use in this presentation. If you have any questions, comments, feel free to talk. And I would like especially thank to Liège University and the committee of the Colloq and organization for the invitation and all support that we have here. Especially thank also to International Atomic Energy Agency and PAS Global Change for the grant. Thank you very much. And all my partners in Brazil that support and sponsor my research. Thank you very much.
Thank you. Thank you. We have time for 1 or 2 questions. I had a question. You mentioned there's oxygenic phosphorus in the sediment. Did you also look at the iron-bound phosphorus pool?
Yeah, well, we have a friend that all have made studies in the lagoon with the fractions of phosphorus, and in the case of the sediment, the iron is not so there's no a big content of phosphorus, and the oxygen we don't analyze the pore water for oxygen and just the oxygen reduction potential in sediment, but it's idea to make more analysis, not for now because I am already finished my almost finished my research, but maybe for another time to quantify iron and also sulfur, because we know that they are important for the phosphorus cycling in the lagoon.
Okay, thank you. Thank you again.
Thank you.
Yeah. Okay. So we need to move on. So thank you very much.
Okay, thank you.
So we need to move on to the next speaker, Michael Beeman, University of California, and he will be talking about rapid oxygen minimum zone shoaling and simultaneous phytoplankton blooms driven by tropical cyclones.
All right, thanks so much for the opportunity to speak here, and it's been a great colloquium so far. So I'm going to continue the tropical theme and actually shift gears a little bit. A lot of this work was done by my graduate student, Brandon Jenko, and then Margot White, who's a grad student with Lahini at Scripps, and then her other student, Irina Koster, was also involved. So obviously we've seen this many times, so we can skip through it. And I'm going to show a different figure here. And this is the tracks and intensity of all tropical storms from this now defunct but great website, Global Warming Art. And what's shown here are obviously the paths of the storms and then their intensity scale on the Saffir-Simpson scale. So the darker blue are tropical depressions, lighter blue are tropical storms, and then the hurricane scale there, 1, 2, 3, 4, 5 being the very strong storms. And so obviously there are these characteristic patterns and where these form and where they go, which may be very familiar to certain people depending on where you live, right, and are affected by these or not. And one of the interesting things to think about is where this intersects with that previous figure. So there is some interesting research that's emerging in various areas looking at kind of the local effects on hypoxic zones, particularly in parts of East Asia in the eastern United States. But I'm going to talk about the large open ocean oxygen minimum zones / ODZs / AMZs. And in particular, these two regions. So the Arabian Sea does experience tropical cyclones, and there's some really great research that's been conducted there. In contrast, in the ETNP, there's next to nothing on this. One really nice global modeling study that's looked at the effects of tropical storms on the ETNP, but it's both the largest oxygen minimum zone, and it also experiences more storms and stronger storms than the Arabian Sea. So we'll focus in on that. And like I just mentioned, it's the largest of the major tropical OMZs. So I'm going to show you some work from an ongoing project and several research cruises. And these are the stations that we occupied on those cruises. So I'll describe those in detail later, but they're shown on this map that shows dissolved oxygen on a categorical scale, color scale. So the reds are below 20 micromolar, the kind of the cutoff for an OMZ following Palmier, and then going up from there. And so stations 1, 2, and 3 are very low oxygen in this OMZ / ODZ / AMZ, and then 4, 5, and 6 experience on average slightly higher oxygen concentrations, but still low. So I'll come back to that. We had cruises in 2017, and that was a nice calm cruise in the spring. There's more upwelling activity along the coast of Baja California. And then in 2018, for better or for worse, we encountered a Category 4 hurricane by the somewhat innocuous name of Bud. And so here's a satellite image of this storm. It's so large, it's actually difficult to see the scale here, but mainland Mexico is actually shown over here, and the tip of the Baja Peninsula is just north of the storm in this image. So it was a very massive hurricane. Category 4. And so we had a cruise in 2017, cruise in 2018, which I'll talk about. And the general study design is we have these 3 functionally anoxic or AMZ stations, 1, 2, and 3 that extend out from the coast of Mexico. And as I'll show, they have subsurface secondary nitrite maximum that we've heard about a few days ago, which are indicative of anaerobic activity. And then the secondary chlorophyll maximum as well with this low light adapted Prochlorococcus. And that's a real focus of our research. And then the 3 AMZ stations extending north from 4, 5, and 6 do not have those features. So they're oxygen minimum zones, but they're not anoxic marine zones, they're oxygen deficient zones. And then I'll talk about station 3.5 in just a little bit. Okay, and so this is the location of those stations, like I mentioned, and then just go quickly through some of these profiles here. But stations 1 is shown in red, station 2 in purple, station 3 in blue here. This shows you oxygen profiles, and so you see that characteristic rapid drop-off, steep oxycline, and then essentially flatlining of the oxygen concentrations from the CTD. We see the nitrite accumulating at depth, and then these dual chlorophyll peaks at each of those stations. And we showed that it is Prochlorococcus there and et cetera. Okay, in contrast, then stations 4, 5, and 6 shown in the kind of light blue and green colors, single chlorophyll maximum, oxygen decreases, but we don't see the nitrite accumulation. Okay, so then station 3.5 we added in 2018, and we did this for 2 reasons. So as I'll show, this station's located right here. it was directly beneath the path of the hurricane. And then the other thing is that it sits kind of on the edge of this OMZ-AMZ transition. Okay, now our main focus in this region is nitrogen cycling and oxygen consumption. We recently published a paper on this. So what I'm talking about today is a little bit of a departure from that, but it's kind of an unavoidable one. So before we left for the cruise, unfortunately, I encountered this tweet and the National Hurricane Center saying that a storm was likely to form in the region where we were going to be. Give you an idea of what that was like. This is the hurricane shown on a wind field map, and the green circle was our first sampling station, station 1. So we went out, sampled that station, and then we had to go back towards shore and basically hide out for a couple of days. And so the hurricane actually rapidly intensified and became quite large as it moved through. It was actually quite beautiful afterwards when we went out to some of our other sampling stations. So beautiful glassy water and sunsets. Okay, so what was the correspondence here? So this figure's got quite a bit of information here. So I'll talk you through it. So basically what's shown is our cruise track in the black line there, and the dates in June 2018 where we were at a particular position. So starting June 10th and then 12th, 13th, 14th, et cetera. The wind speed of the hurricane is shown with the color scale and its position every 6 hours. And there are also dates corresponding with that. And so what you can see is basically the hurricane moved up through our sampling stations and up into Mexico eventually. This highest winds were over in this region here, and it happened to correspond with some of our sampling. So it passed just to the east of our sampling station 2, and then directly over that station 3.5, and also directly over our station 4, but it was weaker at that time point. So Hurricane Bud formed in early June. Follow that northwest track going through rapid intensification, and the forward motion slowed, which is something that seems to be affecting tropical cyclones globally, especially recently. And then, like I had mentioned, it passed close to station 2, directly over stations 3.5 and 4. And we sampled those latter 2 stations about 1 week after the overpass. And so because we have these cruises in the previous year and then in 2018, we have this really nice direct comparison between the two, especially at station 4. And then station 4 also sits in a very commonly sampled area, or relatively commonly sampled area. So we have some additional data from that. And then it turned out that Bud was at peak intensity over station 3.5. So just looking at some data from the ship, this shows you the sea surface temperature from the flow through sensors on the ship. And you can see the color scale on the right, and it's actually quite a bit of variation, right? So, tropical waters, this area is typically quite warm, but you can see that there are some relatively cool waters that correspond with the path of the hurricane. So particularly to the east of station 2 and then right near station 3.5. Perhaps more interesting, the chlorophyll data from the flow through sensors. And what we can see is relatively low for most of the crews, except a pretty intense amount of chlorophyll near station 3.5 and also at station 4. So again, corresponding with where the hurricane passed. And it turns out this is actually a reasonably well understood phenomenon. This is a really nice paper if you're interested in this review article that talks about this. But basically what hurricanes do is as they travel over the surface ocean, they obviously mix up the surface ocean, but they can actually cause upwelling through this phenomenon of inertial waves. And so this figure is talking a little bit about this. And so I kind of think of this as sort of a corkscrew, an Ekman spiral beneath the storm that's generated. And because of that upwelling, it can bring nutrients towards the surface in the wake of hurricanes. So that's shown by the kind of the green dots here. So just to show you that with some satellite imagery, this is animation that's going to show you an earlier hurricane, Hurricane Aletta, and then Hurricane Bud will come through, and then there'll be a little bit of time that passes, and then eventually another hurricane you can see. So this should play here. So that's Hurricane Aletta that's there, and then Bud's forming there and moving through, and you can see the phytoplankton bloom in the wake of that storm. And this is right. So you can see that. And then here's some of these other storms moving up, and you can see that they leave these phytoplankton blooms in their wake as well. So it should start over now. Hurricane Aletta, then Hurricane Bud passes through. And if you look right where the cursor is, you can see that phytoplankton bloom just north of that. All right. So this is a known phenomenon. Tropical cyclones produce phytoplankton blooms, but obviously most of this information is from satellites. And typically these are remote sensing studies of single storms. There's relatively little work that's broader scale. And so to our knowledge, this has not been directly examined in the NTMP outside of a really nice global modeling study. And one of the things that's very interesting is the numbers that they calculate based on modeling and assimilating satellite data. So this is this study by Menkes et al. From 2016. And they looked around the world at the different tropical cyclone formation areas. And the top panel shows the integrated primary production from tropical cyclones. And the bottom panel shows the percent contribution to overall primary production. And so that's the thing to really focus in on and look at the color scale here is that in some of these regions, 15 to 20% of the primary production can be sustained by tropical cyclones, causing these phytoplankton blooms in their wake. And in particular, based on our data, we saw a more intense bloom, so really high chlorophyll concentrations, up to 8 milligrams per cubic meter, and very long, 30-day long blooms that occurred after the hurricane bud. And in most studies, they show a much shorter response. Now, for obvious reasons, it's very rare to have ship-based data on the effects of tropical cyclones. And so we know very little about the blooms, sort of in situ, and then next to nothing about subsurface effects. And this is where this gets more interesting and relevant for the conference here. So these are temperature profiles from stations 2 and 4 from 2017 and 2018. So station 2 is in red, station 4 in blue. The lighter colors are from 2018 and the darker colors from 2017. And so there's really no difference in station 2, but we see a difference in the temperature profile at station 4. And then what's really interesting is the differences in the oxygen profiles. So there's a slightly different depth axis here, and again, the same color scheme. And what we see is that basically the oxygen profile is shifted pretty dramatically, much lower oxygen concentrations, and those oxygen concentrations are lower at a shallower depth. So just to highlight that here, the dashed line shows the 20 micromolar level, and that depth of 20 micromolar oxygen is shoaled by about 30 meters in this case. I'll skip through these in the interest of time. And so presumably what's happening here is that this upwelling is also shifting the OMZ upwards in the wake of the hurricane. And so we're looking at some of the physical oceanographic data to look at that in more detail. But where we saw a really striking difference was at station 3.5. Okay, so what's shown here in the blues and the greens are data from earlier cruises in the region, and then some Argo profiles that were collected afterwards. And you can see that all of those blue and green lines basically show a similar pattern for temperature. Our data from station 3.5 are shown in orange, and you can see how they're shifted in comparison to that. So there's temperature, and then here's oxygen. And so this is a pretty dramatic shift, right? So the oxygen minimum zone is shoaled by about 50 meters in the wake of this hurricane. And then interestingly, if we look at the chlorophyll profile, we see that the chlorophyll shifted upwards, but we also appear to see sort of a small secondary chlorophyll maximum that's forming. Right, associated with this, we also have a secondary nitrite maximum that's also very shallow, so at about 50 meters depth. So in this case, all of our cruise data are shown in gray, except for station 3.5, which is shown in orange. Lower DOC concentrations, presumably due to upwelling, and then very elevated POC concentrations associated with the phytoplankton bloom. So in addition to the phytoplankton bloom, our results indicate that the OMZ shoaled by 30 to 50 meters at stations 4 and 3.5. And so that's a very strong and rapid effect, but I haven't seen really any published information on that. So we don't know how common that may be in the ETMP or elsewhere. It does appear to return to deeper depths later on, but for at least a certain period of time, that places a large amount of labile organic carbon directly above a shallow oxygen minimum zone. And so that should have a number of biogeochemical effects. And then sort of associated with that, we do see this really shallow secondary nitrite maximum and perhaps this formation of the secondary chlorophyll maximum. I'll skip through this here. But essentially then we're following up on this. And so with regard to OMZ shoaling, how frequently does this occur and how long does it last? And so we're looking at that with cruise and float data. With respect to phytoplankton blooms, we have omic data and organic matter data to look at which organisms are actually there, what they're producing. And then the combined effect of this on nitrogen cycling is something that we're really interested in. So we have data on rates and isotopes and multi-omics that we're working through. So with that, I'll take, I guess maybe time for one question and acknowledge funding sources and collaborators.
Okay, thank you. Yeah, we have time for one question. Anyone?
Thanks so much. Excellent talk. I have a question. Do you have an idea about the formation of the secondary chlorophyll maximum?
Yeah, so it's interesting. So I've talked a little bit with Emily Zakim, who spoke a few days ago, and her model seemed there's reduced grazing, how's that to form? But I'm curious if there's also a comment that has to do with basically deoxygenation and the consumption of organic matter, reducing oxygen concentrations enough to somehow allow Prochlorococcus to proliferate. So I think it'd be interesting to see, but I think some combination of the what's happening with microbes and reduced grazing due to zooplankton. And it is a small secondary chlorophyll maximum that we observed there, but it's interesting that it showed up.
Okay, well, thanks again.
So the first speaker, our plenary invited speaker, is Takamitsu Ito. He's from the School of Earth Atmospheric Sciences at Georgia Institute of Technology, and he's going to talk on an estimate of the global dissolved oxygen trend in the last 150 years.
Thank you. Good morning. Can you hear me okay? I assume yes. So my name is Taka Ito, and I'm from Georgia Tech. I would like to thank the organizer to invite me to give this talk, and also I'd like to acknowledge the all of my collaborators to contribute to this result. So my objective here is to assess global deoxygenation trend, which is an easy thing to say, but it's a challenging thing to do. So let's see my next slide. All right. So we know that global ocean lost about 2% of oxygen inventory in the last 50 years, but I want to emphasize that it's approximately 2%. And observational data is irregular and sparse. We have to rely on statistical interpolation method, and these trends are superimposed with natural variability. So estimating these long-term trend is challenging. And on the other hand, our Earth system model struggled to reproduce this trend, both in magnitude and spatial pattern. There are a lot of interesting papers written on this topic. So both observation and models are incomplete, but my take is that they are complementary to one another and make progress by bringing them together. So here's my outline of my talk. So I want to first go through the procedure to estimate the global oxygen inventory trend from World Ocean Database. The acronym for that is WOD or WOD. And I'm going to use a standard method for mapping data. It's called optimal interpolation. There are pros and cons of using optimal interpolation method. It's essentially a smoothing method based on the covariance modeling. And I'll talk about that in a few slides. And then I want to compare CMIP6 Earth system model oxygen trend and the observationally derived oxygen trend. In particular, I'd like to subsample the model oxygen field according to the WOD sampling pattern. So it becomes more apple-to-apple comparison, if you like. And that way I can assess sampling bias by comparing the subsample and full model. So the comparison is kind of a three-way. I have observation and then subsampled model and fully sampled model. And I want to do the comparison for climatology, deoxygenation trend, and regional representation. All right. So my data source at the moment is just solely based on the World Ocean database, and I get the data from WOD Select. The lower left panel here shows the distribution of number of bottle data from WOD, and we see that there are a lot more observations in the Northern Hemisphere close to the population centers, and there are uneven distribution. On the lower right side, this is a time series of profile counts in different measurement techniques. So the bottle Winkler data is the yellow, CTD oxygen data in red, and in the last 10 years or so, we have a strong ramp up of BGC cargo profiles. So over time, the sampling density and the measuring techniques are also evolving. So these are the challenges. Let's see. The method, I think I went one slide too ahead. Go back. Okay, great. So I'll be using bottle data after 1965 and CTD data after 1987. I'm not including the Argo data yet. We are not quite ready to integrate BGC Argo at that moment. And I would like to use the optimal interpolation that will bring the data from the discrete profiles to grid. The discrete data looks like this in June climatology near the surface, and after optimal interpolation, we have a smooth and field. And we do that for monthly climatology and also oxygen anomaly from the climatology in a 5-year running mean sense. So the overall a little more detailed procedure is here. So I take data from the World Ocean database. And the nice thing about this is that it also has a quality control flags in it. So we only use accepted oxygen profiles, put it in a global monthly 1 degree or 1 degree bin, and then first apply optimal interpolation to get the climatology. And then after that, I subtract the climatology from the bin data, apply 5-year running mean to get this running mean O2 anomaly, apply optimal interpolation again to get the smoothed annual resolution oxygen anomaly field, and then from that we can get the inventory trend. So there are a lot of references for optimal interpolation. There it's a classic method, and I use Gaussian covariance function for the mapping. So what that means is that if I have an observational point, its inference decays away from it according to the Gaussian function. So it's a simple and straightforward calculation. So, and I'd like to do something similar for the model. So I take the CMIP6 historical runs, degrade to 1 degree or 1 degree monthly domain, and I can simply time average it to make a full model climatology. I can also apply 5-year running mean to get the oxygen anomalies, and I have a full model O2 trend. And then we'll add additional layer to bring the model a little bit closer to observation, where I take the sampling pattern from the WOD profiles and subsample it, subsample the model output. What that means is I intentionally remove information from the fully sampled domain to get something that looks like observation, and apply optimal interpolation to get the climatology. Once I get the climatology, I can get the anomalies, apply 5-year running mean, apply smoothing again through optimal interpolation, and then get the subsampled to trend. So I have these 3 products, and I can compare climatology, and I can also compare the deoxygenation trend. So this is a climatology at 100-meter depths in December. World Ocean Atlas is upper left. This is my climatology based on World Ocean database. Of course, World Ocean Atlas is made from World Ocean database data. So these two should look close to one another. And the other 6 panels are based on the model output. And the name of the models are down here. So overall, they look similar, low values in low latitudes, and then it increases towards the high latitude. If I subtract the World Ocean Atlas values from the model outputs and also my own climatology, we can see the difference. And I find this interesting that units, sorry, the fonts are small. This is plus or minus 80 micromolar. So this is very large biases in the model. And I find interesting that the tropical thermocline tends to have too much oxygen at 100-meter depth. And it seems like a common feature in across the models. And so this is sort of the state of the art. We still have a long way to go. And the problem gets even more substantial if you go to the deeper depths. This is a 400-meter climatology. So close to the core of the OMZ. Again, the model bias is on the order of tens of micromolar, and the Southern Ocean, low latitude, upwelling region seems to have quite a strong bias. So we knew this going in, but still on the modeling side, we have a long way to go. With that in mind, I'd like to look at the inventory side. So this is from surface to 1,000 meter integrated oxygen inventory. World Ocean Atlas and my climatology has about 55 petamole inventory. And the model estimates range plus or minus 10%, 10 to 15% around that. What I also want to look at is the difference between the blue bar and the orange bar. The blue bar is the subsampled model climatology, and orange bar is the full model. So at least in the context of the model, subsample model, oxygen inventories are within about 4% of the full model value. So the optimal interpolation is giving me a reasonable estimate for the inventory, climatological inventory, despite with the biases in the model. And then more difficult challenge is to try to map the deoxygenation trend that is annually changing inventory. So this is a binned oxygen anomaly data from 1991. I just randomly picked this year. So this is how sparse it is. So if I do 5-year running mean, I'm going to lose the time resolution of the data by averaging from 1989 to 1993, the 5-year running mean. But I can increase the spatial coverage a lot more, and then it allows me to apply optimal interpolation to fill the global grid like this. So basically, I can do this year by year to build time varying oxygen inventory. And linear trend. So I took a 1967 to 2019 period, take a linear trend, and I made a map for the upper 1,000 meter oxygen trend. So the red color is a linear trend that's decreasing oxygen over time, and the blue is in increase. And I try to match the color scale as close as I can to the Shimiko et al. Result from their 2017 paper. The difference also is that the published result is plotted in 0 to 1,200 meters. So there's a slight difference in depth range. But doing this, I see generally a similar pattern and magnitude of the deoxygenation, except that the tropical deoxygenation is much reduced in my result. That seems like a main difference here. In my calculation, it's about 1.5% loss over 50 years. Shimiko et al. is about 2% loss over 50 years. Mine's 162 thermal per decade, and there's 258. So that's the kind of difference I'm getting. I'd like to then look at the time series and compare that to the model estimates. So here I have two panels. This is a time series of oxygen inventory anomaly in the units of thermal, and it's a global. Left panel is a full model, and on the right side panel is subsampled model. The black solid line is the observation, my estimate of the world ocean database, and the colored lines are model output. So, so some model, especially in the fully sampled version, shows comparable trend to observation. So this is encouraging. I think we are starting to converge, and also the sampled version is really interesting. That you might see the trend is a little weaker, and this is somewhat expected by mapping the sparsely sampled data set. And also the noise, the interesting noise. You might see some zigzag shape of the observation, and some of the model has a matching zigzag pattern. I want to highlight this a little bit more. So in the next slide, I just pick one model to make this comparison with a single model. This is GFDR ESM4. And the blue line is the subsampled version of GFDR model. Green line is more smooth, fully sampled model. And the black line is the same observation again. And I can just match it by this peak in the late 2000s matches with this observational peak. And then there's another peak in late 90s. I see similar peak here. So, and this is not just, I didn't just cherry pick one model, but there are a couple of models that does this behavior. And so it seems to show that some model are actually reproducing this internal noise that is present in my observational estimate, but I think it's an artifact of sparse sampling because the full model output doesn't have this peaks. And so I don't think this is a coincidence. And another thing that I've been worried about for some time is this long-term change in the profile count. That so on the lower left panel, I'm showing a monthly profile count as a function of time, and I have a lot of observation back in 1780s. It's a borrowed data, and then it starts to decrease after 80s and towards 90s, and then we start to have CTDs come in. So it made me curious because that decrease in the sample count somewhat coincides with the start of the strong deoxygenation, isn't it? I mean, there may be no reason to make because this is really a change in concentration, but it made me worried. So we can start to play some manipulative experiment that I can randomly drop observation in an earlier period so that I can normalize the profile counts to about a certain level close to 1990s and maintain it throughout the period. And then I can recalculate the oxygen inventory trend calculation to see what happens to this time series. So normally, this is where I would ask people in the auditorium to make a guess. But I can't really see people's response from here. So it could be no change, or the trend could increase more steeper, or trend could decrease flatter, right? By purposefully reducing the number of samples, but make it more consistent throughout the time period. So here's the answer. I reduce it to about the 1990 level and throughout, and I find a similar deoxygenation trend. So this was reassuring that this is just not an artifact of changing sample count. I get more noisier time series in the earlier period where I taper down the sample count, but this seems to be a robust feature. And also I should say that I only subsample, reduce the sample size only in the Northern Hemisphere. There's plenty of observation. I didn't dare to take out profiles from the Southern Hemisphere. Okay, so I still have a few more minutes. So I'd like to now look into the global inventory trend again. And I made a bar chart so I can compare this model, subsampled model, and the full model. So this is linear trend in the units of teramole per decade, ocean database, and then 6 models here on the right. And the blue bar is the full model, and the orange bar is the subsampled model. And I use the same color for the observation because observation is subsampled real ocean. So, so what we see is that subsample, just looking at the yellow or orange bars, subsample models still significantly underestimate observed deoxygenation trend by a significant amount. And also another interesting thing is that the subsample trend in my calculation, comparing the blue bar and the orange bar, always the orange bar is shorter than the blue bar, isn't it? So it underestimates the full model trend. And this is somewhat expected because in the optimal interpolation, when I don't have observation nearby as particular grid point, that grid point tends to have 0 anomaly because the inference from the observational data point decays like a Gaussian function. So if you are away from observations, I can't put any value in, so I tend to put 0 in there. But we can start to look at, since I have a map, I can start to look where the disagreement is coming from, disagreement between observation and model, but also fully and a subsampled model. Okay, so this is a sort of a box plot. I divided global ocean into 11 boxes, and each boxes I calculated inventory trend. So the color scale is more blue color is a decreasing trend, and the red is increasing. So, so please use that to interpret this. So the negative trend, this is observational tile here, World Ocean Database, seem to show decreases in almost every box. And these other panels are model. So this is where we can see some interesting differences. So some model, especially in the Southern Hemisphere, show increase. So it's really models are having a different behavior. One region that all models are consistent is North Atlantic. Every single model at least have a negative sign and similar magnitude relative to the observation. Significant decrease in the Southern Hemisphere, I find that's quite interesting, but also these are the data poor regions, right? And so this is a model, and in next slide, I have subsampled version of the inventory trend. So in general, the sign of the trend doesn't change between full and subsample model, but the amplitude gets a little weaker when I subsample it. So I want to look to a few regions using my remaining few minutes. So North Atlantic seems to be a good area where models all agree to decrease oxygen, and magnitude is somewhat comparable to ours. So this top row is subtropical, and then the bottom row is subpolar. The left column is full model. Observational line has to be subsample always, but the models are fully sampled. And on the right is a subsampled model output. So the nice thing is that subsample model generally capture the trend that is in the full model. There are one or two exceptions that this orange line significant zigzag noisy behavior that is not present in the full model. But besides, overall models, a subsample model capture the full model. And the trend magnitudes are somewhat comparable. So I have a bar chart here. This is subtropical linear trend and subpolar linear trend. So the blue bar and the orange bar are similar to one another. So this is relatively dense region, data dense region, and my optimal interpolation does a really very good job of. And also this is a good region because a couple of models are starting to overlap the observational trend. And in the subpolar region, some models are substantially stronger and some models are weaker. So the model is starting to bracket the observation. So this is a region where we can really ask, which model recaptures observation and what are the differences. And in contrast, Southern Ocean is relatively data poor, and also it's one of the darkest blue color box. That means the trend is strong in the observational data. And what's interesting here is that there is this zigzag shape again of the observation, and fully sampled model doesn't really have that noisy behavior. But when I subsample it, I can actually match by eye these three peaks in some of these model output. So the major sampling noise are visible in the subsample model, and I think this has helped to interpret maybe these peaks are spurious result from the undersampled ocean. So yeah, just a few slides left. So this is the comparison of the linear trend. Again, comparing the blue bar and the orange bar, there's substantial difference between the full and subsampled models. So my gap filling method is not doing very well in the Southern Ocean. The data is so sparse that probably my optimal interpolation is not a good approach to capture the trend. And so I have a suspicion that there's a strong trend about almost 30 teramole per decade, but we have to really interpret this with caution. I plainly am not convinced that this is a real trend. Okay, so to summarize, in this small analysis, I found about 1.5% loss of oxygen over the last 50 years. And it's the uncertainty would overlap with Shumiko et al. Result, but I see less tropical deoxygenation in my calculation. CMIP6 models are getting closer to observation than previous generations that we saw in the previous publications, but still underestimates global trend. North Atlantic is one good region that the model starts to bracket the observation. So in conclusion, models are not perfect, but I believe it's useful for understanding observation, especially subsampled model can illustrate this noisy behavior of my observational time series, especially in the Southern Ocean. To conclude, I understand there are interesting initiative moving forward. There's a global O2 data set and Atlas developing. I'm really interested in collaborating with you and doing a comparison of observational estimates. I think it's important to do independent group estimating this deoxygenation trend and do a standardized comparison. I'm also working on integrating the new observation, especially BGC algo, into the global inventory time series. We are not there yet, so I don't have result to present, but hopefully in the future we have something. And at the end, but not the least, I believe reproducibility and open access is important. So all of the results, the observational results that I showed, should be reproducible because the data set is the WOD select. You can put that in Google and you can access the data. And also the scripts that I use to generate this data is available from the GitHub site. So if you're interested, please check this out or shoot me an email and I'm happy to go through what we've done. So with that, I'd like to finish my presentation. Thank you for your attention.
I think we could have one question before we go to the next speaker. Benedict, you can come on up. Andreas? Oh, no, go ahead. We'll have two questions.
Thank you. Thank you very much, Taka. This is great to see that, and the fact that you make it available is really, it's great. I don't see you anymore. It's weird, but I was wondering, when you subsample the models, you show those like variations that come out of the models. Did you try to leverage the fact that some of those models, not GFDL, ESM4, but the others have members, and that actually you could disentangle how much would come from really the subsampling from whatever variability there is in the model, knowing that the models, those models don't reproduce the observed variability at the right timing?
Yeah, I understand. I understand what you mean. I only used one realization from each model because honestly, it's just a lot of work to download this and do this mapping exercise. But yes, I understand the noise is really coming from the sort of convolution of sampling, irregular sampling pattern and the variability that is realized in the model. So I think if, and CMIP6, many models have multiple members. So yes, I think it's possible to do exactly what you said and assess sort of this randomly occurring variability in the model and how much that's going to make it into the final time series. I think that'll be a useful thing to do.
Thanks very much, Taka. One question. Well, I'm some issues with the your second conclusion on the call for transparency, and I'm working with on Zoomkill right now that we also repeat that in a more or maybe clearer way with CMIP6 model data. But I think even CMIP5 was very good in the upper oceans. So laterally averaged. The patterns are all over the place, and that's still the case for CMIP6. So I don't really see any improvement, I must say. And also the global deoxygenation is pretty much the same from CMIP5 to CMIP6. So I wouldn't say there's a big improvement. And well, you concentrate on the upper 1,000 meters. That's where earlier models agreed on average, laterally averaged, globally averaged also pretty well. I think the main discrepancies on the deep ocean, and you showed the Southern Ocean, which is the entry to the deep ocean, or to a large part. And I think that's really where models have problems, but maybe also the data coverage is not good enough. But I think we really have to resolve that in the future together. And I very much welcome your effort. But I wouldn't say the models are getting much better so far, unfortunately.
I appreciate your comment. I think for the upper, maybe like below 300 meters, the model starts to degrade its performance in my experience. So yes, I think it's still a big problem. And I think I showed that there is actually a lot of, in a lot of regions, we have disagreements. Maybe North Atlantic and actually, I think Long et al. Paper showed that in the CMIP5 models, also there's a reasonable overlap in the North Atlantic. So maybe North Atlantic is one good region. But yes, I agree that we still have a long way to go.
Thank you very much. We have to move on. Our final speaker of this morning is Benedict Blackledge, and he's from the University of Bristol in the UK. And also, I'm reminded to tell you that if you want to go to the panel, the diversity and equity STEM, it's in the professor room, and they have sandwiches. So it's really a good motivation to go and participate in that panel as well. So you get lunch up there.
Okay. Just those two. Yeah. Okay. Okay, can you hear me okay? Right, great. Just a quick apology. This is a slightly old version of these slides, so if there is any odd formatting, I will try to explain it, but do feel free to quiz me on it afterwards. So apologies for that. So thank you very much, Professor Ito. That was a really nice introduction to some of the things I'll cover in this talk. And thank you to the organizers for giving me a chance to talk about this current phase of some of my PhD research, which is being broadly on the ocean atmospheric influences that go into oceanic oxygen variability. So I'm just going to not use the Schmidt-Co 2017 figure in this case, and instead use this nice example from Strammer and co-authors. Just to point out that whenever we try and observe oxygen in the real ocean, if you observe for a long enough period of time, you can find a really broad range of modes of variability, putting aside any force changes for the moment. And in the case of the Pacific, these can range from a few years to, of course, a couple of decades in the case of the North Pacific. Modulations around the sort of typical concentrations that you might be observing. Now, many of the processes that go into setting these oscillations in concentration are quite well understood. However, a lot are really not very well understood still. So it was interesting to me to ask, well, what sort of sets of these mechanisms might be tractable for study with modern Earth system models. Specifically, these were models associated with CMIP6. So we've been hearing a lot about the issues that models, marine biogeochemical models present, and I agree with all of the issues that have been raised over the week. What I would propose, though, is that models which have been well evaluated and documented with respect to other climatic variables, namely things like ocean heat content, do have value. And just as a quick aside, I would just add that some of the motivations and methods that have gone into this work came out of a CMIP6 data hackathon that my institution ran around about this time last year. And if anyone's interested in learning more about how to run one, we produced a paper on what you would need to do to set up that sort of a workshop. So come to me afterwards if you're interested. So just to introduce, I'm only going to be talking about one model. The approach that I'm describing is going to be generalized to a set of models that we have available. The one I will be talking about in this case is the Max Planck. So the MPI model, the MPI ESM 1.2, which is a higher resolution version. And I just thought I would take this opportunity to, this is not in any way qualitative, but quantitative, and I'm afraid the metric, the scale is wrong as well. But I just wanted to point out just that when we refer to oxygen dynamics, these dynamics at the global scale really are just that. You have these large gradients established by biogeochemical processes, which then get advected around. You can begin to see the footprint of wind-driven mixing in the Southern Ocean and the higher Northern Hemisphere as well. And I just wanted to highlight that the fairly pretty self-portrait of this particular model for an oxygen field. So the approach I've been using was actually first used on the IPSL model for CMIP5 by Damien Cospel and co-authors in their 2019 paper. And the approach is to take oxygen subduction into the interior. So we're using a transport decomposition, so fluxes of oxygen from the surface mix layer into the ocean interior, which is composed of a kinematic term, a skin, and a mixing term. The kinematic term is essentially a composition of the advective terms, but also the motion of the seasonal mix layer itself as well. And the mixing term is, as you would expect, it's driven by the vertical and lateral diffusion properties. So this is I'm not going to go into the details of the numerics. Suffice to say that we apply these to monthly mean outputs, and we include a respiration estimate that's quite crude, certainly at the moment, but again, I won't discuss that. The decomposition is applied to generate a thermal component. So we apply this transport decomposition to the O2 sat, the solubility, and also just the oxygen field. And from those, we can then derive a, quote, non-thermal transport term. So something that is not necessarily attributable to changes or alterations to transports in the solubility term. And just for the purposes of time, and definitely not to do with the fact that some code broke before I came to this conference, I'm going to be discussing the advective terms, specifically the horizontal advective and the mixed layer subduction there. But again, come to me afterwards if you wanted to talk more. So what we're evaluating is evaluating terms at the mixed layer base, which is a natural surface to look at if you're interested in thinking about exchanges between the ocean interior and the surface. And there's a reason for that. We can start to think about the footprint of the atmospheric forcing as well as the ocean dynamics, which is, I'm interested in the interaction between the two. But this method's Achilles heel really is that we are not accounting for redistribution. So this is very much a partial technique. Although I have got plans for a more complete form with a more targeted modeling study. So what I'm going to present now is just an overview of the oxygen variability. So now whenever I talk about variability, it will be purely a standard deviation, just to define that beforehand. And then I'll present case studies essentially of these kinematic transport terms for this particular model. And any data that you see now is going to be fully de-drifted, so we've controlled for model drift, and it's from the pre-industrial control run from this same said model, the MPI HR model. So this is just an overview of oxygen variability from the models that we have available locally in my institution. So variability varies is a phrase I like to use, but what we see is the colored models are the ones that I've been evaluating, blue being, red, sorry, being the HR model. And we tend to see that these tend to sit above throughout much of this. So this is a zonal variability, sorry. They sit above the rest of the ensemble for much of the world's ocean, but typically sort of more suppressed, a narrower range of variability towards the higher latitudes. And this is the same metric, but now just showing the spatial variation of what that looks like. And again, thinking back to that little animation, what we're really seeing is in the ensemble variability there is essentially the motion of those strong gradients. And then to the right, I just wanted to highlight again what the HR model looks like compared to the rest of the ensemble. Again, we see there's that slightly elevated variability, suppressed, so more minimal variability in the Southern Ocean. So to get into what these terms look like, I will just explain the slightly odd formatting briefly, sorry. So these are time series of the mixed layer subduction term. The faded lines were simply included to illustrate the seasonal variability, and they are accounted for on the left-hand axis. So the right-hand axes are my metric of interannual variability at this moment in time, which is quite simply a yearly mean, just to remove that seasonal signal. And these are global integrals. So these are globally integrated mixed layer fluxes in units of petamoles. So these are petamoles per month. from here on in, and that will be the same for all the time series I present. So what we find is that, well, unsurprisingly, the non-thermal component integrates to be a very much smaller term than the thermal component. And overall, if we account for both and the sort of attempt to produce a sort of typical oxygen subduction metric, we find about 0.542 petamoles per year, which compares favorably to the COESPERL 2019 study. But does differ a little bit by, I think, 0.5 petamoles or so. I may estimate numbers, so if you want exact figures, I can give them to you afterwards. Apologies. So this again is just the mixed layer subduction term. I'm just going to skip over that. So this now is the horizontal term. Now, unlike the mixed layer subduction, what we are doing, which essentially is providing oxygen into the ocean interior as we would expect, horizontal transport seems to remove it. And this is a typical property that we see in similar studies. It's a result that we've recaptured from Deming-Cospel's original study, and the values compare favorably. So while we derive a value of a little shy of 0.6 petamoles per year, if it's a sort of total negative transport, the Deming's, well, it's slightly less than the COESPEL 2019 study, which was around about 0.8. I should just note that these are also comparable with similar observational-based estimates that were done by Portela and co-authors. I would highly recommend that you go along to Esther Portela Rodriguez's talk tomorrow at 10:15, I think, where she will be covering that work in more detail. Their estimate of the similar quantity was very much less, but again, negative, around about 0.18 or so petamoles per year. So this starts to introduce this idea that the models are getting the signs right, they're getting something right, but perhaps what we're seeing is the introduction of some of these sparse sampling issues that Professor Ito mentioned. And I just thought I would map these out to show what the variability looks like over the globe. And what is it? So this is mixed layer subduction as a standard deviation. So here I've removed the effect of seasonality. So this is just the interannual variability in this term. Now, this is for the soluble component, which, as I pointed out, was unsurprisingly very much larger than the non-soluble. But when we try and compare the relative spreads of those, what we find is this, as yet unexplained, I'm afraid, difference between the hemispheres. We find this extremely greatly exaggerated variability in the northern hemisphere in the solubility component, but for the southern hemisphere, when we can start to find regions where the non-thermal component actually exceeds the solubility component in terms of transport. And again, for the horizontal advection, this is essentially, as you would expect, energetic regions of the ocean are where you tend to get the most enhanced variability in oxygen transport. But what the global integral hides is the fact that there are regions that do tend to put in oxygen in a sort of, in a net sense at least. So here I've taken the same time series that I've been showing and just integrated them in time. So this is essentially a map of individual points and how much oxygen was put in or removed essentially at that point. And again, what we see is this competing effect by definition of the thermal and non-thermal components, but also again, this hemispheric asymmetry, I guess we could call it, between where oxygen gets put in. But again, it is by no means true that horizontal advection removes oxygen from the ocean interior everywhere. There are regions where it tends to be the dominant and the net input of oxygen. So just to quickly summarize, again, I would highlight the provisional and preliminary nature of this work, and I again apologize for the poor formatting, etc. here. But I would argue that this form of decomposition framework does actually provide a way of making inferences about the sorts of variability we can see, the interannual variability at least, between the surface and the ocean interior. And while the terms presented here are incomplete, we're beginning to get some sort of a suggestion, at least, that the interannual variability may for some terms be a quite important fraction. And I would propose that the CMIP6 archive does represent, all issues considered, a useful resource of ready-made experiments to understand and draw inferences about these sorts of experiments. So this is very incomplete, and I'm happy to talk about what I'm doing in the near future, but thank you very much, and I'm happy to take any comments. Thanks.
Questions?
I have one in the online.
Yeah, go ahead.
Okay, I was wondering if there a simple, well, nothing is simple, but is there a way to tease out the oxygen vertical stratification strength over time and relate that to that of thermal vertical stratification?
I haven't done that, but that certainly sounds interesting. I didn't hear the first bit of your question, sorry. Just.
Sure. If there is a higher vertical thermal stratification over time, one would expect perhaps that there is also an oxygen vertical stratification in terms of strength and how, you know, tight vertical stratified is the ocean in the upper ocean with respect to oxygen.
Yes. So I do not have those plots with me, but yes, if you have a region that warms, you do reduce the solubility of the oxygen, but you will also generally introduce a negative or reduce the transport, often, but not always. But I haven't actually looked into that in enough detail yet. So, but yes, I think that sounds right-ish.
One last question.
So just one quick question. Did you include the vertical mixing term in your subduction estimate? Because this looks like...
Yeah, so this is currently incompletely, yeah, the answer is yes, in the full decomposition, yes, we do, yeah. Yeah.
I'd like to thank all the speakers for great presentations this morning.
Okay, I think we will start to not kind of delay the whole day, but I'm very happy that I'm here, the moderator of this panel on diversity and equity in STEMs, and together with a great panelists with me, Claudia Jesus Redin, Jody Rama, Maciek Telczewski, Sarah Wolf, and Mitya Safari Fakaraini. I'm sorry. I will introduce them a little bit more in a second. But before that, I would just like to present some hard facts on gender equality and ocean science. And for that, I just a couple of slides, which was produced for the Global Ocean Science Report, which we published in 2020. And one important chapter there is really the human capacity, because in the end, that is driving ocean science, that is driving the ideas. And in this Global Ocean Science Report, we are not only focusing on human resources, but of course as well on the capacity and showing differences in the world, but also opportunities, hopefully. So this Global Ocean Science Report was produced by an editorial board of 12 members, 5 female, 7 male. We had 2 co-chairs, one from Africa, Jacqueline Nuko, a great woman and leader, and actually for women in ocean science, where there's a great women researcher network as well in the Western Indian Ocean Pacific. And Indian Ocean, I mean, and we had 35 authors, but we collected data really from 45 member states of IOC. And so, though that's not complete, as you can also see on the map, but we have a quite good overview about what is happening in ocean science, what is happening in terms of gender equality, because actually those 45 member states produce more than 80% of the science publications we have. So just going quite broad, national numbers of ocean science researchers vary between less than 1 to over 300 employees per million inhabitant. And these ratios are actually don't directly relate to the GDP. So it's not the more you have money, the more you invest in ocean science. Some countries really step over the average. And for example, Portugal, you have a lot of ocean science. And there's more equal gender balance in ocean science and science overall. So female scientists comprise about 39% of the researchers, while in natural science, it's only about 29. So we are doing not so bad, but there's still a long way to go. And so this challenge is really possible to achieve. Some countries are really doing a lot, and you can see that, for example, in Ireland, you have a lot of women working in ocean science, and also in Germany, in the Dominican Republic, for example. Certain countries you also see, like, it's quite surprising that there's so many women, but why? That's a question we couldn't really answer yet. There's no real pattern where we could say why it is. What we can also see, female ocean scientists are increasingly talking to the world. Female participants account for 29 to 53% of total conference participants, but this really depends on the category. There are categories like ocean technology, observation, where we really still have a lot of work to do to actually achieve gender equality, equal participation, and not only the quota, but really equal participation. And I think, and we try to find out, for example, as well, in whether we could get numbers on the senior level and so on, but actually a lot of countries still don't know where they stand in gender equality in ocean science. And so there's a step to be taken that we report where we are to then also improve. What is also quite obvious, there are regions where women are dramatically underrepresented in ocean science, and this is quite dramatic actually in the Pacific. So there are regions where we have to work a little bit more, and I'm not going into detail here, but I think also now looking after COVID-19, we are still in there, but we have to assess what is the impact actually really on the careers of female researchers, and we have to support them. We have to create an enabling framework, and I know Claudia knows much more about that than I do, and has a great presentation. And so I will actually pass the floor to her just for a very short presentation as well. She's a senior program officer at the ERC, a geotechnical engineer, originally from Portugal. And at the ERC, she also coordinated the ERC gender activity group, and really is a leading force in that. Thank you.
This one? Yeah. Okay. So thank you for having me. It's really a pleasure to be here and to talk about gender equality. So just to get the facts right, why do we care about gender equality? Well, actually, women are not a minority. Women make up to half of the humanity. Despite this fact, there is no country in the world till this day that has reached gender equality, even if there is no evidence that gender is linked to distribution of talent, but rather instead of this, on how resources and opportunities are distributed. So now I'm going to go a little bit about what the ERC does. So we fund frontier research, and we have mainly three schemes that are PI driven. So that is a starting grant, consolidated grant, and an advanced grant. And we have what we call eligibility windows. So for the starting grant, that is focused on 2 to 7 years after PhD. Consolidated grant are 7 to 12 years after PhD. And then in advanced grant is a little bit different. We don't have really an eligibility window, but we do ask our applicants and our panel members to focus on the last 10 years of their career. However, extensions of the track record period that is considered is possible due to career breaks, and I will come to this a little bit later. So we started, the ERC was funded in 2007, and since its establishment, we have been focusing and taking a lot of actions to ensure fair and equal opportunities to all candidates, while keeping, this is very important, excellence as the sole evaluation criteria for frontier research. Some of these actions have focused on what we call this eligibility window that I was mentioning just before. Personally, I think the action that we've taken in 2010, that is the first yellow one there, which was to give us a possibility to extend the eligibility window for women, for mothers, by giving 18 months per child that was born either before or after the PhD, but also to fathers. So if they've taken parental leave, so paternity leave, they can also extend the eligibility window by the real time that they have taken off. Then we've done taken other actions, such as, for instance, to remove a section that we had in the CV that was called scientific leadership, just because we saw that that was really a source of imbalances when assessing candidates, not only men and women, but also those that were less eloquent, so to say, in how they wrote. So the language skills, or even if they were natives or not English-speaking natives. In 2014, we introduced a CV template. That was actually a request from our panel members to make it easier to assess CVs. And finally, the feedback was quite positive from the applicants. We also introduced in 2015 another reason to extend this eligibility window or track record period, which is time taken off to care for sick relatives. Again, this is not targeted to women, but we do know that women are usually the ones taking upon them these type of roles. And then in 2016, we initiated a series of training sessions on unconscious bias, actually implicit and explicit bias, to panel members, for ourselves as staff, scientific officers that coordinate the evaluation panels, but also for our governing body and the management. In 2020, we organized, the usual ERC annual conference was focused on sex and gender dimension in frontier research. We recorded the whole event, so it's actually still online. There is a link here, so you can just go and listen to some of the presentations. And in 2021, we introduced also an update in the proposal template, where we actually have now a section where we invite candidates to report in a structured manner how COVID has impacted their career. We know we've all been impacted by COVID, but some people have been impacted quite differently from others. And this is what we want to capture here. Now, about the progress that has been made. So as a result of these concerted actions, and to be honest, I will just tell you here up front, I don't think there was one action that produced significant effects. I think it's a cumulative effect of concerted actions that were taken. What we see on the left side is FP7, so is the framework, so it's one of our jargons, but actually it's a time period from 2007 to 2013. And on the right side, we have Horizon 2020, which is 2014 to 2020. And here what you see is the women representation as panelists, applicants, and grantees. And what you see, let's start with the panelists, is that we managed to increase the representation of women by 6% in the last framework program. But also, even if I must say, it's quite hard to recruit women. So we have like 58% acceptance rate of women and 70% of men. So it means that for each woman that we have in the panel, we had to work a little bit harder, but that's okay. Then regarding the applicants, there was also an increase of women applicants by 4% and about 10% as grantees. So let's look at the success rate. Again, FP7 on the left and Horizon 2020 on the right. What we have managed to achieve is actually the confirmation that talent distribution is not linked to gender. We have finally achieved comparable success rates between men and women, and we are very happy about this. But what could be done more? Well, from the side of the ERC, I have to tell you, we are really open to suggestions from panel members, from the scientific community, from applicants. Some of the changes that we have implemented were actually coming from you. So the communication channels are really open. So please just send us your ideas. But also, it's not just about institutional changes and actions. Of course, there is the national and institutional policies, and I have listed here just a few as an example. But now I want to send the ball to you also about your own individual choices, because that at least you are in control. You're not necessarily in control of the national policy on parental leave, but you are in control of other things. For instance, you are in control of who your life partners are. And for that, I mean your personal and professional partners. Your share, the share of unpaid workload that you accept. And by that, I mean not only at work, but also at home. And we know that imbalance is quite huge. The strategy for your own career. You should be in charge of the strategy for your own career. And here I just ask, is a rhetoric question. Do you have one? So think about it. Your career ambition. So this is not about competing at home with your partner. Not at all. That's not healthy. But it's about getting the importance. So the importance of your ambition should be at least as equal as your partner's. So there's no reason why one career should take priority over the other. How do you organize work-related travel and personal life? Are you generous and kind with yourself, or you just say, oh, actually, I'm going to stay home because, you know, now there's this hybrid option, so I'm going to stay home. You will miss out on the networking. Parental leave model. Yes, one thing is how much you can take, but also how will it be shared? One thing is what is available, but what will you actually do in reality? The childcare strategy. So there's the formal ones, the institutional one, but there is the informal one, including who takes the first step for when the child is sick. Is it going to be always the same parent that stays out of work? And this is very, very important. Create your own support network. You know, the people that you go to when you're not doing so well, when you have doubts, when you need some push, want some encouragement. They don't really have to be in your professional field, in your side. It doesn't have to be your co-authors, but can be people that you trust and that you can just brainstorm and get some ideas and support. And then I cannot leave without saying this, sorry. And also who is elected and makes decisions. Please vote. It's not just about national governments or local governments. It's also about societies. Every time you are invited to vote, please use that opportunity. And that's all from me. That's a sort of a take-home message.
Much for this very inspiring talk and really setting the scene for hopefully some lively discussions. I also invite you actually to go to the Padlet because there's a survey and we have some questions for you, just also to kind of evaluate here the audience and who's listening and who wants to be part of this discussion. I'm very happy, as said, that I'm here with a great panel, and the first speaker we already heard, Claudia. We also have Mircea, who is a master's student here in Liedge in the Erasmus Mundus program, and she's really instrumental in now building as well this young researcher network, Liedge. And I think we will all hear from her a lot, but I have also some questions for you. Then we have Jody Rummer, an associate professor at the marine biology at the James Cook University. We have Maciek Telczewski, the director of the International Ocean Carbon Coordination Project, and Sarah Wolf, a PhD candidate who's also quite active in really social media and training, and also to really get up the young generation, the young girls. And I just would like to really, and I all invite you to vote on the Padlet. You have the QR code on your badge. To kind of, if you all could make a short statement, what you think is the main obstacle right now, really prohibiting gender equality, diversity, equity in STEMs, and maybe particularly in your field. And maybe I can start with you, Sarah. Oh, sorry, put you on the spot. It's not on, I think. All right. Can you hear?
Hello? Okay.
Sorry?
All right, sorry.
On the Padlet, you have the surveys and the yes. Exactly. Thank you very much.
Okay, so the question is about current obstacles, and I can only
Yeah.
speak from my experience. I'm a fourth-year PhD candidate at Oregon State, and I'm a first-generation college student. And so I think that a really important obstacle or a pervasive feature of my academic journey is just not knowing how higher education works. And I think that we talk a lot about science communication and making analogies for our research, but I think it's equally important to communicate how tenure works and how academia works, because those are barriers to people who don't feel confident in this space as you know, people who don't have parents who went to college. So I think that that's really important to also include in the science communication conversation.
Yeah, if you want to go next, yeah.
Yeah, I'm fine. Going next. Hello, everyone, and thank you for inviting me to this panel. I think I will take this opportunity to expand the diversity, equity, inclusion outside of gender only. And I know it's important, and I know we've heard this beautiful introduction about gender mainly, but I guess, you know, there are similar aspects of our life, like, you know, ethnicity, age, which will become an issue very soon in Europe, as you know, religion, perhaps, and many more that need attention in terms of DEI. And I think talking about all of them together makes it a little difficult to be specific, obviously. However, in my opinion, and from my experience over the last 10 years, trying to coordinate various groups and task teams, etc., the biggest obstacle I see to achieving diversity, equity, and inclusion in STEM would be a very basic thing, which is basic education. A lot of those groups that are minorities in this room even, they miss out because of the very lack of access to basic education, primary and secondary education. That's well before they even think about university. And the second, which is kind of follow up on the first one, in my opinion, is lack of access to higher level education due to the rising cost of access to such education at the level allowing them to then become members of our community in sciences. Thank you.
Hello, everyone. I guess personally, a lot of the boundaries that I've experienced have been related to imposter syndrome and feeling like I don't fit in. And so I think, you know, for many, many years, a lot of us females in science, and I definitely want to echo that it's diversity and inclusion is not just about gender. Sexual orientation was another big one for me. But we would almost put up an armor and try to conform to what we thought maybe a scientist should look like or sound like or act like, or maybe the approach that a scientist should be taking to a problem or even communication. And so I think that a big shift that we are seeing, and I'm definitely taking on, is for me, being a really great role model means being authentic and being transparent and being exactly who I am. And I think that I can lead by example with that. And then that's also how we start to address those systemic problems at our institutions that lead to those inequalities and inequities that are part of this issue. So I guess to summarize is kind of embracing that imposter syndrome and knowing that it's really common, no matter if you're what gender fluidity, any aspect of diversity, that we're all having it and embracing it and discussing it.
Yeah, thank you very much. I think really looking not at some specificities, I mean, looking at a person, each person is individual and each should be also valued in their own, in their own qualities. But I still think that, and though I agree with Magic, I think it's important still to have some concrete on specific items, for example, gender equality, because if you are getting very big, it's also a big thing to chew. But before, maybe we can go to Mitya and then go back to Claudia. Yeah.
Thank you. Thank you as well for sharing your perspective. It's also resonating from what I believe as well. I think one of the biggest obstacles that we have ever faced in terms of achieving diversity and equity in STEM is the imbalance of self-awareness and self-belief that has been shaped over time in our society. And if I would like to share from the perspective from developing countries, for example, there are so many like clashing with the societal issues, like about the culture and religions, like I have already mentioned before, and you know, like the issue, like the forced child marriage still happening in so many islands in developing countries, and this is also one of the biggest driving force that I would say that makes most of the women, if we will talk about diversity in terms of like gender, do not continue their study until the higher education. And it's like in Indonesia alone, there are like 270 million people in our country, and they have like lack of access to educations in everywhere. And even like the Internet of Things, it's not widespread in every island. So I think this kind of like our job, like our responsibility, that how do we extend our arms to this potential pool of the people, and we're not only talking about the female in this case. I would say like the fisherman's son, the farmer's son, and how do we can also thinking about how we can introduce the youth representative in the science ladder career. I think, yeah, it's almost clashing with societal issues, I suppose. Thank you.
Yeah, thank you very much. I think we see big discrepancies between different countries and different regions. I think what Claudia as well, and I leave the word to you. In Europe, we are at a certain point, but it's still, I think we have to set the bar high to really to grow there. And maybe Claudia, I mean, you mentioned a few of these obstacles, but what do you think is still the major one?
You cannot have 50% equality at work if you don't have 50% equality at home.
Yeah, thank you very much. I think. No, but you're right. And there are some more questions on the poll, I don't know, on the survey. And before I also open to the floor, because I guess there will be many have some questions, but what do you think would be like, if you want to go from national, institutional, and your personal choices and yeah, movements which should be made, what are the key issues we should move forward, in which we should move forward within the next 10 years to really, I think, having a sustainable ocean, because we won't achieve that if we are not tapping on all the brains we have. So what do you think would be some of the key national, institutional, and private choices to make in the next decade? Who wants to start? Magic?
So on the national level, it obviously varies from country to country, and we only have the influence over that by voting. So I strongly agree here with people. There was voting brought up yesterday. There's voting brought up today. I think this is something that we need to promote, and we need to choose this active participation whenever we can, as was said. But I think that the national educational programs should be aimed at, when possible, at those minorities that we are talking about, this underrepresented. And by aimed, I mean they should be given perhaps more focus to become to be given an equal start. At the same time, and I'm now speaking from my experience, I'm Polish, and I was brought up in Poland, which, as many of you might know, is not the most diverse, equitable, and inclusive country even on this continent. Unfortunately, education on the benefits of having diverse, inclusive, and equitable society, group, class, team should be given a lot of emphasis. We in Poland, at least in our educational system, have never been taught what you can gain from having a person with a different ethnicity, different sexuality, a different age in your group. And this is something that I think should be done on the national level. At institutional level, I think that we might be thinking of bringing some sort of chief diversity officer kind of person or committee that is responsible for those aspects. And this need to be people with passion, because this is a very emotional topic often. And the management should be involved in creating goals and be accountable for meeting those goals by this committee. And on personal level, I think, and again, this I can only say from experience, as I'm not an expert on a topic in terms of academic expert, you need to, I think I try at least, to get exposed to the situations that these minority people are exposed to often. And by saying that, I mean, there is a museum of blind people in Warsaw, in Poland, and you spend an hour there walking around the city without any sight. This opened my eyes, so to speak. This is amazing. And what was brought during the presentation earlier is that I, for example, spent a week trying to do what my wife does every day while having a career. Oh my God, that was a tough week. I had no time to spend on improving my own qualities during this whole week. This showed me that we need to do things differently, because I do have time to go and have a training. She doesn't, because she has to do this and that. And I agree completely that what you have at home, you then bring out, and this is specifically about men-female diversity situation, but I'm sure there are examples for all the other minorities. And finally, whenever possible, try to get exposed to complaints, so to speak, or issues brought up by those underrepresented. Go to meetings, go out to the streets if needed, because these people are shouting things that you perhaps don't understand. Often we exclude groups from our society, in my opinion, because we fear them. That was the situation with gender, at least in Eastern Europe. And as soon as we realize that there is no enemy, there is no devil in those aspects, we start embracing them. And I think getting in this conversation is something we can do every day. Thank you. And sorry to be too long.
Okay. Yeah.
I think I'll just share one, because there's a lot of us, but I think something that I think about, and I've talked a lot about with my advisors, is sort of the putting the money where the mouth is in funding. And I think that a large part of that is undergraduate research and paying undergraduates. We can't expect them to work for free and then not be able to tend to their other lives, and it's just a huge disadvantage. So I think that that's one very tangible thing as labs and as PIs we can really try to do, compensate fairly for the work that our undergrads are doing. It's a great experience. I wasn't paid in my undergrad, but I also, you know, worked 2 jobs. So it makes things easier. And I think it increases retention down the line, and it makes people feel like they belong more and they're valued, which confidence and imposter syndrome is huge in academia. So that's just one tangible thing, I think.
Yeah, thank you. Maybe you just go down the table then.
Sure. Yeah, I definitely would echo what Sarah has mentioned here, because I think that, you know, sort of the 3 elements that we can look at from a personal, institutional, national, and global level would be recruitment, support, and retention. And yeah, at that level, you know, students from around the world might not have that opportunity to just go and volunteer in a laboratory and not get paid to get experience. Some students do have that luxury, but a lot don't. And so I guess from my personal perspective, thinking about the recruitment, support, and retention, how can I recruit more diversity into my team so that, and you know, I'm very guilty of saying this a lot, but recruiting, supporting, retaining diversity in STEM leads to happier scientists and better science. I'm going to get better science out of it. So it's a huge win for me and my team's going to be better as a result as well. But we have to think about, like, how can we create opportunities for those that might not have those opportunities otherwise? So that's kind of at that individual level. At the institutional level, we have to have systems in place that are addressing these issues as well. And kind of getting off of that recruitment, support, and retention, because there are always issues about that. Our institution set up, I don't know if there's any Star Wars fans around here. We set up JEDI, and that stands for Justice, Equity, Diversity, and Inclusion. And we're constantly addressing those issues that are affecting our capacity to recruit, our capacity to support, and very much our capacity to retain and keep all these amazing scientists and make sure that they feel supported. At the national level, yeah, I definitely echo it's got to be at the voting. We have to have leaders in place at the national level and even at the high levels at our institutions. We have to be voting for leaders that are going to take JEDI issues very seriously. And globally, you know, we're doing that now when we are attending international conferences and making sure that there's support to include as much diversity as possible. So better scientists, happier scientists, better science as a result. And I think it's win-win regardless of the level that you're looking at.
If you want, yeah.
Well, let's start with the institutions. So feminist movements in the 19th century thought that education for women would solve the issues of gender equality. It didn't solve it. On the 20th century, it was about access by women to institutions. It didn't solve it. So 21st century movements are about changing the institutions from inside, like having JEDI groups that really move and change the things from the inside. Now, JEDI cannot just be about forwarding emails about how interesting this is, please read it. It has to have indicators. So you have to be accountable as an institution for what you're doing. If you claim that you have a policy, please make public your data and your progress, whatever your policy is, but make it public.
Thank you.
So national, institutional, and personal, right? So I think when it comes to national, it should be like efforts from different multi-stakeholders, that government, private sectors, and public sectors as well. And I would say that what we can do is how every member state, like every country, can really provide the opportunity of women. If you are graduating from high school or university, you have like the equal opportunity to go, not only for going right away to the creative industry, which is very common, that they just being like a small entrepreneur first, and like time goes by and they don't think about continuing education anymore. But this kind of like encouragement that from every multi-stakeholder, nationally speaking, is very important. And second one about institutional, I really echo as well from what Keith said about the national, the program, the educational. And for example, in our program, like Erasmus Mundus, they assure that they will receive like 40% at least that coming from women. And they also receive like people that coming from different countries. Like we are 32 people in the cohort with 20 countries representative. And so I think this kind of like approaches that we can tweak in. I think we need to like provide more scholarship to these people so we can study here. Like for example, for myself, like if I not get the scholarship, I wouldn't be able to live here in Europe and study. And this is such a great opportunity that meeting a lot of people here, like being involved in this colloquium, for example, it's just incredible. And imagine how incredible it would be for like more people out there that maybe they have some dream in their heart, but they just cannot be having access to this kind of opportunity. And from the personal, I would say that would be coming from each person of us. And like, let's start small from this room, that anything that we can do in order to encourage more involvement of women or like youth that coming across the science, I think that would be wonderful also in the long run. Thank you.
Thank you very much. This was brilliant. And I think you summarized quite well. It really starts with all of us individually being role models, being mentors, encourage engagement. We did have a poll and I find the results actually quite, unfortunately, not very surprising, but we had those two questions like, have you ever experienced any problems in your career due to the fact that you are a woman? And still 50% had that. And I think it shows that there's still some work to do from our side, while only 12% man. And I still think that's too much. I think nobody should be, because of your gender, whatsoever, should have any problems. It's not about that. But there is this discrepancy, and I think everything should be at 0 and the lower bar should be 100. So I hope we can all like really move forward in that. But I will also leave the floor to maybe questions, give the floor the opportunity to ask some questions if there are any. Yes.
Hi, thanks for sharing all of your experiences. It's great to hear that everyone's sort of tackling this from different angles and sharing all of that. I'm curious, so you all talked about the different efforts that are sort of happening at different levels, and especially the ones that are happening where you are involved. And I'm curious about the success rate of those strategies and maybe what's worked and what hasn't worked. And if you see the institutional change you're looking to make, as a graduate student, talking to your advisors and trying to get grants for undergrads. And if you're seeing that retention that you're trying to get within JEDI, like, are those things becoming real, or is it still just, we're pushing really hard and there isn't a lot of response?
Maybe I just quickly start because I have a very good example actually from the ISIS. They didn't have any policy on gender equality. And then they started 2-3 years ago, and now the executive secretary is a woman. So now they really put attention to it. They really made the difference in that. But it was because it's quite often actually in the fisheries sector, you have women as well quite underrepresented. And so there they paid attention to it, and there it was successful. But I think you probably have a few examples. I don't know. Jody? Yeah?
Okay. I think a few examples of where we are already seeing successes. And yes, I definitely want to echo that we can't have these, like JEDI in place without having some benchmarks that we're aiming for. But when we do set up a conference or a seminar series and just really looking at those ratios and making checks and balances with what we say is important to us and what we say are our values and what we publicly announced, that we are actually reflecting that. There's also, and we shared it within our group as well, but maybe we could make it available. A really good colleague of mine published a paper in PLOS Computational Biology a few years ago, and it was 10 steps for gender equity in science. I can't remember the exact name of it. And one of them was that she's stopped agreeing to speak at conferences if they didn't have something in place. And that was a real catalyst for a lot of what we have been talking about and even putting this panel together as well. And so if you have really key scientists that are just saying, no, I'm not going to be involved unless there is something in place to address equity issues in the sciences, and then people wake up. So those are a couple elements there that we have actually started to see change with.
Somebody else? Yeah.
I can talk about on a small scale, like in our labs, and I feel really fortunate to work for people who are looking in the mirror and seeing, okay, how are we training students? How am I doing a good job at this, especially in the last 2 years? And so it has been a changed, rule in our lab that we no longer have students just paid for dishwashing and volunteering for research. They're now paid for all of their efforts in the lab. And whether that means that my advisors are seeking out separate summer scholarships, or they're just a little more in tune to those emails of undergrad scholarships, I think now, because they know it's really important. And both of my advisors recently became administrators, which presents its own challenges as a grad student. But they're really keen on collecting the data, because we can't address a problem in our small institution if we don't know what exists. So I think collecting those metrics is really important. Unfortunately, I don't think we have enough of those metrics, but you can see some little turnaround,
That's a word.
Yeah.
Thank you for the question. And I would like to know the answer to your question at institutional level, honestly, because I have no clue how this actually works and what are the real success stories there. On the international coordination, it does work. We do look, and when I say we, it's not only the panel I'm running, but other projects which you might have heard of: SOLAS, IMBER, IOC, working groups, and others, many others. We always look at the parity very closely, not only gender, but also geographical distribution of people we invite to training, to conferences, people we pay for to go to places. And this pays off in a sense that I very often see people we've invited 5-7 years ago to a summer school or otherwise now holding positions, not positions of power, but positions of seniority, and expanding, conveying the DEI to the regions they're coming from. So it does work at this level, but this is definitely much smaller level than institutional level where formalities are and administrations are involved. Thank you.
I also just wanted to add one thing. I think it's important, not only parity, but also parity in leadership. And that is something where I also really pay attention to, and always try to encourage women to move forward and say yes, because there's support. At least we try to deliver the same support. Also within the UN Decade of Ocean Science for Sustainable Development, there is one program focusing on women, and I have high hopes as well that they will try to make a change and will come up with some global and regional initiatives really helping empowering women, particularly in leadership positions, because that is how we then also really make this pipeline not leaking anymore, but straight. But yeah, another question.
Hi, thank you all for your time and for coming to this. So my question is mostly maybe at like the department or institutional level. And I was wondering if there are any discussions around reforming the tenure process, for example, to reward DEI work, because a lot of the effort falls on women and minorities to make these policies come forward into fruition. And so a way to maybe alleviate the pressure because it distracts you from your science if you're working on DEI stuff. And so I was wondering if there was discussions about that at your institutions. Thanks.
I don't want to do all the talking, but that's such a good point. It's when on gender equity in the sciences started to arise, and it was from a very famous study out of Massachusetts Institute of Technology, MIT, in the States. And they put in a lot of measures in place to really address gender equity. And fast forward several years into the process, a lot of these very high performing female scientists at MIT said, you know, there's still an issue because now I have to be on every panel. I have to do all this mentoring because I'm still in the minority, and they always want to have a female or, you know, someone of a diverse background on these panels and workshops, et cetera. So that was still an issue for a long time. And so I guess that is definitely what we're addressing at the institutional level, is not putting all of that extra work because we still don't have those numbers with diversity. It's ongoing, definitely, but really trying to share that work. I guess what I would also add to that is making sure that the training opportunities, we've got lots of leadership, adaptive leadership training. We have diversity and inclusion training, heaps of different workshops and programs, but making sure that it's not just, say, the females that are doing this extra work to build our skill sets to tackle this issue. We can't be trying to solve the problem without the other, say, half of the scientists or researchers. They're with us to help us with this problem. And so making sure that those opportunities aren't just taken up by the people that feel the most affected by them.
Yeah, thank you. Yeah.
Yeah, I totally agree with your point. And I have observed in some institutions that these DEI groups or JEDI are actually led by postdocs or people with non-permanent positions, which I think it's really sad. And it just gives an indication on how not seriously this is being taken by the institution. Because if you're serious about it, you have to engage also the hierarchy of the organization. So the diversity needs to be reflected in the group, because otherwise you're asking the people that have the least negotiating power or pressuring power to be actually leading this battle. That's not fair. And that just says a lot about the organization.
Okay, there are a lot more questions, but we are a little bit running out of time. Okay. Okay. Yes.
Hi, thank you. I'll make this quick. It's really more of a comment. I'm sorry, I can't see your name from here, but I liked that you pointed out the idea of hiring a diversity officer, because I always think about in science, like if you were hiring a modeling professor, you would never hire a committee of economists, even if they were really smart and thought a lot about modeling, to come fill that position, and so many of these issues are deeply structural and can be placed in a historical context that you'd want to hire an expert who potentially even has a PhD on the topic to come work and do the labor and get paid for it. So yeah, thank you for the time.
Yeah, very good point. I think a lot of the gender focal points probably including me have a different background and just try to keep up with what's going on.
Thank you guys for your input. So my question is, when you're coming to equitability, are the people who are affected more have a historical background or influence? So when it's a race, they're already behind. So if it's the women, maybe they had 2 years out because of pregnancy or kids. If it's us, our equipments are less, 10 years behind. So how do you come to normalize this in your making out the equitability? Because still, even in the race, you're still behind as you start. Thank you.
Who wants to take that? Yeah.
So I think you're asking about how to level the playing field. Yeah, that's not easy, of course, because if I think about the ERC, that's too late, because this is top level grants that we're talking about. So you need to take measures before. I think at some point quotas and dedicated funding, it's the only way to solve the issue. Again, I think this is for very specific situations. You cannot ask quotas to be implemented all the way through, because otherwise you are undermining the credibility of the program and the credibility of the awardees. So I think in that case, that's the only way. I agree with you. Where if you start from a very low level, there's no way you're going to be competitive with all the rest. Yeah.
Yeah. I would say it's actually related as well with Jody said about capacity training. And probably in the future, we can be more creative in creating initiatives as well that we can provide to the people that is going to be recruited in the long run. And maybe some kind of like competition so they can be level up to hit that measures. So they know that there are like communication skills, like capacity building training, or like our training, for example, that, okay, they have like different skill sets that we can take into account, even though they seem like they don't come from a well-recognized university, for example, from the first hand, which is also happens a lot, like in many countries. So I think we need to be able to tweak some kind of like training in terms of non-formal education in order for them to be naturally and slowly and maybe geologically timescale speaking until they can be slowly level up and hit that point.
Yeah, maybe I also think like especially capacity training, focused capacity training, that is where we can make a difference, probably quite often very locally and very, as Claudia said, very specific points. But I think it's good to start, and then we can scale up and creating a capacity, and hopefully so that this capacity also stays in the countries and doesn't need to move away if they don't want, because that's quite often then. And also then really they're having it equally, helping to have this enabling framework for different gender, for different countries, for different nationalities, religions. I think that's something where those international organizations are also, it's our task to move that forward, and also with conferences like here, trying to get people with fellowships as well exposed and to learn. And I think that's what we can offer at this point, I think, but a long way to. If there are no, yes, there's one more person.
I would just be curious to hear if any of you have had discussions in your efforts to explore diversity, to go to challenge sort of the surface level idea of diversity of, we accept in people who look different, but act like that we already have decided is how you have to be, versus an approach to diversity. It's actually making space for people with different ways of being. I'm curious if that's factored into your conversations at all.
Thanks. I can do my best to try to address that. So our department established a core values committee. And so we have regular trainings with the entire department. We can't make them mandatory, but they should be. And we've had speakers come and talk about the warming of the environment. And there's a researcher out of UW that has a lot of papers and things about how warming the environment can make things easier for people in science. And so while it seems kind of silly that like weekly coffee hours make a difference in a department, like having those interactions and meeting people where they are just on a normal basis has really helped our group. In addition to these trainings, we go to these trainings, we talk to each other, we share experiences, and then we see each other every Tuesday at 2:00, and you can just chat and just have this like warming of the environment is a really big goal in our department. And I think that we're trying to make the space for that, and it is part of the conversation, but it is difficult to change.
I can make a quick comment.
Yeah.
I would think that we have to just keep doing more, even if we are in that space where we are addressing these issues at our institutions, within our own research groups, or even at national levels. We have to do those checks and balances with ourselves as well. And it's not in the poll, but I'm not sure how many people have taken the implicit bias test or an unconscious bias test online, which you can Google it and you can find it, but it's something that I do regularly because I'm finding that I still maybe use language that I guess insinuates that I have an unconscious bias or stereotypes. Maybe if I'm writing a letter for recommendation for a student for a PhD position or a job, that I really want to make sure that I'm, constantly aware of where I might need to grow and improve. So, even those of us that are in that space regularly, we're constantly doing those trainings and checking ourselves. So maybe that kind of adds a little bit to what Sarah's mentioned as well.
Yeah, thank you very much. But I think now it's time to close this panel. I really enjoyed it, learned a lot. And I just would like to thank the panel for being here with us during lunch. Thank you very much.
So I guess that we can reconvene in 10 minutes. So at 15 minutes past 2, and then we will have to respect the timing of the talk. We have the first visit of the brewery at 4, and normally we should finish at 3:30. Yeah, okay. So see you in 10 minutes, just a short coffee, and then please be back.
Normalement, oui. Oh, I see. It was that one. Yeah.
We should really start. Yeah, I think we should start like now. No? I think I will.
Wow.
Yeah, bring people down. You want me to
Have you
start?
seen that?
I think we'll start. Hello, good afternoon. I am your substitute for Hernan Garcia. Karen Limburg is my name. Today, because we have this very important social event, which is to go visit a brewery, we are going to keep people on time. So we're going to get started now. And for those of you, including the folks online, I'm going to hold everyone to time quite strictly. So if you want to have questions, you have to speak for less than 15 minutes. And I'm going to give everyone a 5-minute warning, 1-minute warning, and then we're going to turn off the lights or something. No, I'm just kidding about that. But we do need to stick on our time. And so for those of you who are online and going to give presentations, I will just speak in the microphone and say it's 5 minutes. Okay, does everybody understand that? The rules, the ground rules for this afternoon? Okay, very good. So I'm very pleased to introduce Pablo Truco Piñata.
Thank you. Yeah. Okay, thank you, everyone. I'm super happy to be here, quite excited. I want to say 3 things before I start. The first one is that I'm finished my PhD this year, so I'm looking for jobs. If you like what you see here, or if you know that something that can be related, I will appreciate it to hear about it. The second one is I want to thank all my collaborators and also my sponsors, because I wouldn't be here without them. And the third one is, I'm sorry about the title. I'm really not good at that. No, it's quite convoluted and confusing, but what I'm trying to do with this work is just to try to kind of, it's not moving. Simple, answer a simple question. The Southern Ocean on the annual base, integrated in the annual base, is behaving like net autotrophic or net heterotrophic. Would you ask like the whole Southern Ocean? No, I'm going to point out which region, but before that, a little bit of context. Looking at carbon, I know that we are in oxygen, the conference, but looking at carbon, 40% of the ocean CO2 is uptaken in the Southern Ocean. Is quite significant. The amount that goes in this region is not fixed in time. We have a lot of variability, interannual, seasonal, but also it seems that there is forced by a decadal variability that you've seen that, for instance, in the 90s, it was a period of relaxation of the uptake of carbon in the Southern Ocean, and then the next decade, reinvigoration of it. So it's a matter of subject of discussion still, but it seems that it's related with the position of the SAM that is modulating this more longer timescale variability. And also it's not quite homogeneous around the whole Antarctic region. No, if you go and sample in different front positions, you will find different uptakes. No, and this is a work by Bushinsky that they try to account for different products between SOCOM and SOCAT, and the uptake divided by front. So this is variable in time and in space. Oxygen, again, one of the most displayed figures, one of the two. No, I don't know what is the score so far, but this one is the work of Smithko. In the Southern Ocean also, we have that there is a loss of oxygen. But I would like to also present another one from his work that is a vertical comparison between the expected change due to saturation in red and the observations in black. If the change will be due just solubility, the two lines should be just matched perfectly, but it's not the case. There is some other things that are impacting in the change in the vertical content of oxygen, and is one of the things that I will try to target my discussion at the end. So this is the region. If we zoom in a little bit, is around this area. You should have some color, but it's between these black lines, between the 40 south and 70 south. Why this region? Because in this region we have a really deep mixed layer depth and an intense formation on subantarctic mud water. Why the subantarctic mud water is important? Because it's the one that connects, it's a pathway for the carbon that is being uptaken in the Southern Ocean to get in the interior. Both, no, like the solubility carbon pump and the biological carbon pump, no. So testing how efficient this process is happening can give us an idea of how the system works related with climate change, no. The data sources, I have two. This is the floats that I selected in this region, and is oxygen temperature salinity from those floats, and we constructed a time series of 13 years from 2008 to 2022. We have 97 floats, and we have roughly like 6,000 profiles. The other data source that we use is reanalysis from ERA 5 to select wind, sea level pressure, and relative humidity for the position of the floats. And those two data sets are the one that I combine and I do my analysis. We also separate divide the analysis by front position. This is the climatology from Kima North Sea. You have the subantarctic front, polar front, South Antarctic circumpolar front. So I group the data in these fronts, north of them, 1, 2, 3, and this is the color that I'm going to use to refer for what is happening. The method is a quite simple method. The principle is that you have the observation from the floats and you subtract, you calculate the physical parameters that can influence this variability of the observations, and what remains should be an proxy for the residual, should be a proxy of net community production. Schematically will be something like this. You have the atmosphere, the mixed layer depth, and below the mixed layer depth, you have interchange inside and outside of the mixed layer depth. These are the observations. Also the same, but in the bottom of the box for Ekman pumping and entrainment. So if I calculate these three, and then I subtract it for the rate of change of the observations, I get with net community production, but also with the physical processes that I'm not incorporating in this stage of my analysis. That's something that we will do later, and I will tell you about that too, plus the errors. No, Dasha spoke about that yesterday, and the air sea fluxes is component by a term that is due to solubility and the wind, and you have also the component of bubbles, large bubbles and small bubbles, and there is plenty of parametrizations that deals with these bubbles component. We use Emerson because it's the one that gives us the most conservative kind of fluxes, but there is plenty of other parametrizations. Entrainment is the rate of change of the mixed layer depth multiplied by the gradient of oxygen in that layer. And we resolved Ekman, no, zonally, and then with that we estimated the Ekman pumping and multiplied by the same gradient at the base of the mixed layer. So having these three components and separating the data in these three fronts, we looked at our analysis. The first result that I want to present is the delta O, is the measured oxygen minus saturated. If you have a negative value, is undersaturated. If you have a positive one, is oversaturated. And this graph, what I'm showing you here is the three fronts, like the results in a time series that goes from October 2008 to October of 20, and integrated between one summer to the other summer, because I want the seasonal of the onset of the summer to the next summer. And one thing that you can see from this graph is, well, the values go between 30 to minus 30 for the northern area, the red one. For the blue one is the middle one, 30 to minus 30, and the the other one is 60 minus 60 is the one that changed. Three things is the seasonality that you can have from the 3-time series, that in the summer, in the northern one, you have is oversaturated, and in the winter is undersaturated. And it's kind of the same for the rest, but the degree of undersaturation decrease in the movement, the way that we move to the south. And if we fit a linear regression, we can see that the rate of change for the three areas is quite similar, decreasing in the degree of desaturation of -0.2 or around -0.2 micromoles per kilogram per year. This is the evolution of each of the terms of this equation by year, integrated by year. So there is a lot of things in this graph. So I'm not going to mention all the things that we are seeing over here, but I want to point out that the diffusion, that is the component of the RC that is due to diffusion, is one of the fluxes that is dominated in the annual cycle and is changing through the time. And this is the one that is dominated the net community production that we are estimating. From this graph, what I subtract is what is the resultant of this integral of the end of this year, and that will be the evaluation, the value of the annual net community production. And by multiplying by 1.43, that is the ratio between carbon and oxygen for this region, I end with the equivalent of carbons. Going from the south to the north, the southern region, the annual net community production is net heterotrophic, yeah, and this is due
5 minutes.
4 minutes?
5.
5 minutes? Okay, that's good. This is a float that is an example of what is a float in this region, no? Because we have plenty, but this is a float that tend to track around this region. We have depth and we have time, and we have the percentage of saturation. Here in white, I'm highlighted the under synchropolar deep water associated with this isopycnol, and in pink is the mixed layer depth. So this quite undersaturated water is quite close to the surface. And when we solve the equations for the influence on this and the other parameters, this signal is the one that dominates overall. And that's why we have a region that is most in the balance of an annual cycle, because it is the balance. A net heterotrophic environment. If we move a little bit north, we don't have too many whole years to actually compute for all the other years. That's why we have these gaps. But we have in 2015 and 2016 net autotrophic system, but then it shifted to net heterotrophic for the rest of the years. No, again, another float that it was drifting around this region, and this is again the upper circumpolar deep water, but we have another one that is quite disparate, that is Antarctic intermediate water, that is quite close to the surface and outcrops over here. No, so that's also that we think that is influencing these values, and the one that it interests us the most because you have the mud water formation. Sorry, region, the most intense is this one. Oh my God, sorry. Is this one. And here we have a net autotrophic system most of the time, but what you can see by eye is that it tends to decrease for the whole period that we have a calculated value that is close to 0 over here. No, so something that is might be happening that the system is.
That wasn't me.
So it was a thunder? It was. Yeah, well, I'm almost finished. But yeah, something is happening that it seems that the system is shifting, being producing large quantities of carbons to decreasing the capability of carbon production in the annual base. So as conclusions, the mud water formation region, so Antarctic zone, behaves net autotrophic. We have a mean of 3.3, but changed a lot, and it seems that it's decreasing. For the other one, is net heterotrophic with different, but I want to talk what is going to be happening next. We want to upgrade this model to resolve the density layers at the isopignal surface associated with this one to test the efficiency of the model in sequestering biological carbon. Incorporated vertical eddy diffusion, that is the two components that I didn't incorporate in this analysis, and also the advection of the fluxes. I don't think that is going to be changed massively. We are integrating in a big area to account for this advection, but it's important to incorporate it because a lot of that happening around the ICC. Then something that I'm doing right now is compare these results against the annual nitrate drawdown by floats. Hopefully that is going to be like, if they match, they will give us a lot of support of what we are finding. Then those certainties that I have evaluated the wind data already with a meteorological station. And then the last one is to compare this product, the NCP, against net primary production from satellite to estimate export ratio. So that's what I have. I still have time?
Great, thank you. And good staying on time. We have time for one question. Yes.
Excellent talk, Pablo. Really good. I have a question, or maybe you have an insight. With respect to those 3 zones that you have and the change in productivity or decline in productivity, would you suspect that the decline you see is because the zones are expanding or shrinking or moving, and you keep them constant in your analysis?
I do think that it might be more related with what is happening with the mixed layer depth, and that there is not a reset, because what I have here is how the mixed layer depth is changing the depth during winter from the region, and the period it tends to be shallower. So there is no mixing, enough mixing that maybe is not supporting for the net community production for the last year. But that's just an hypothesis. I need to explore more. But that's a good point, and I have to keep in mind.
Sorry about that. I can figure out my timer.
Okay, thank you.
Okay, first of all, I would like to thank the committee for allowing me to give this talk in this wonderful event so far. And I would also like to acknowledge the effort of my co-authors in developing this study. My name is Paula Cipardo, and I work at the Marine Research Institute in Vigo in Spain. And I would like to show you some preliminary results that we have with the study that we did on long-term variability of oxygen in the Northwest Iberian coastal upwelling system. As we all know, there has been an increase in the number of hypoxic areas in the global ocean. Some of these areas are included in the main boundary upwelling systems. There have been studies on long-term trend variability of oxygen in these systems, with different results, from not finding any trend at all, like it happened in the Benguela current upwelling system, to find really high long-term decreased trends in oxygen, like in the California and Peru current upwelling systems. So we wanted to add more data into these systems by studying the long-term variability of oxygen in the Northwest Iberian coastal upwelling system. This is, I don't know if I change, yeah. This system is the northern extension of the Northwest African upwelling system, and it's a very peculiar system because the water that upwells here, which is the Eastern North Atlantic Central Water, forms north of our region of study, but pretty close to it. So it means that the water that upwells here is well oxygenated. And we were thinking that it would be interesting to know if there is any long-term variability or long-term trend in the oxygen in these relatively high oxygenated waters. So the Eastern North Atlantic Central Water is, as any other central water, is defined as a linear relationship between temperature and salinity. And to study the long-term variability of oxygen, we focus on the isopignal 27.1 kilograms per cubic meter. And we didn't have a long-term time series of oxygen. So what we did was to compile data from local sources for local organisms, national organisms, And we also get data from international databases. We were lucky to cover the period of 40 years and from the 1970s, and a relatively wide data in front of the Northwest Iberian coast. The results of this data compilation was that in the central water at the isopignal 27.1, during these 40 years of measurement, the temperature and salinity present an interannual to decadal variability, but none of them shows any long-term trend. On the contrary, as you can see in the plot, the oxygen does show a long-term trend of around minus 0.31 micromoles per kilogram per year. So the question is, what's causing this decrease in oxygen in our water mass? Well, there are three main mechanisms by which the oxygen can change in the water mass, and I will be presented those mechanisms here using this plot. This is a vertical distribution of oxygen from a work done by Aran et al. 1994, and is from a north-south section along the eastern North Atlantic and passes by our area of study. And it covers also the area of formation of the central water, because the isopignal 27.1 outcrops in the northern part of the section. So the water mass is formed and then sinks until it stabilizes at its depth, at its corresponding depth. So the first, as I was saying, the first one of the three mechanisms that we are going to study is change in oxygen at the region of formation. So to check or to test this hypothesis, what we did was to get data of sea surface temperature in winter in the region of formation of the central water from the analysis. And what you can see in the plot is that there was an increase of the sea surface temperature in the region of formation of around 0.14 degrees centigrade per decade. And this must be, this probably will imply a decrease in oxygen. So we estimate the oxygen saturation in this region of formation by assuming a constant value of salinity of 35.5. And the trend, the decreasing trend that we found in the region of formation in oxygen saturation was minus 0.06 micromole per kilogram per year. So yes, there is the change in oxygen in the region of formation are causing some decrease in our water mass. But this decrease in oxygen only accounts for 90% of the oxygen decrease that we found in the central water. So it's a possible mechanism, but it doesn't cover all the decrease that we found. So we need to keep looking into the other mechanisms. So other possible mechanism could be related to change in the primary production, at the local primary production in front of the Northwest Iberian coast, because an increase in primary productivity will lead to a higher amount of organic matter in the water column, that in turn will lead to an enhancement in the remineralization processes that consequently lead to a loss in oxygen in the water mass. So to test this process, to see if this process is happening, what we did was to complete data from a work from Alvarez Salgado et al. In 2002 for the period 1982 to 1999. This is an estimate, these are estimates of net primary productivity. It's very difficult to have data measured primary production. So we just estimated it and we completed for the 40-year period. And as you can see the plot, it seems that there is a decrease in net primary production. So in any case, this can be a mechanism of decreasing oxygen in our water mass. So, oh, I don't know what I click, but anyway. So what it could be another cause for this oxygen decrease is oceanic circulation. This is the third mechanism that can affect oxygen in the water mass. So let's take a look at how the circulation in our area of study is, or in general in the North Atlantic. So the Northwest Iberian Peninsula forms part of the subtropical gyre, is affected by the subtropical gyre. that together with the subpolar gyre are two of the main features, dynamic features in the North Atlantic. And the third one, important and relevant dynamic feature of the North Atlantic is the meridian overturning circulation, the thermoline circulation, the circulation of the water masses. And both the subtropical gyre and subpolar gyre are really relevant in determining the vertical distribution of the Atlantic meridian overturning circulation, as well as the intensity of its transport. So we have to take into account the variability of these three main features to see what was going on in circulation during our period of study. So the subtropical gyre and subpolar gyre present an interannual to decadal variability that from the work done by Hakim et al. In 2011 is related to the amplitude of the wind stress curve. In the way that when we have a strong amplitude in the wind stress curve, we have a strong circulation in both the subtropical and subpolar gyre. The subpolar gyre expands its work in the North Atlantic and southward, and this allows for fresher and cooler water to be transported by the gyre to the eastern North Atlantic. On the contrary, when we have weak amplitudes of the wind stress curve, we have weak circulation in both gyres. The subtropical waters intrude into the North Atlantic and allow warmer and saltier water to be transported into the subpolar gyre. This variability in the subpolar gyre has been translated into an index defined by Hakim et al. In 2005. And positive values of this index indicate strong circulation in the subpolar gyre, while negative values of this index indicate weak circulation in the subpolar gyre. And this could account for the variability between gyres, but we need to also consider the variability in the thermoline circulation, the Atlantic meridian overturning circulation. And there is an index for that was defined by Kaiser et al. In 2021. And again, positive values of this index indicate higher transport than usual in the Atlantic meridian overturning circulation, while negative values indicate weaker or lower transport than usual in the Atlantic meridian overturning circulation. As you can see in the figure, there was a slowdown in the Atlantic meridian overturning circulation since the beginning of the 20th century, that has been really rapid from the 1960s on. And this covers most part of the period that we are studying, which is this shadow area that I put on top of the plot. So let's compile or let's put together all this dynamic information with the change that we see in the properties of the central water. And as you can see, from the 1970s to the more or less mid-1990s, there was an intensification in the subpolar gyre circulation that if I go to the variability in temperature and salinity, I can see that there was a decrease both in temperature and salinity, and this could be related with this more influence of subpolar waters into the eastern North Atlantic. At the same time, the average value of oxygen during this period was relatively higher than for the rest of the period that we have data. And this would again imply that, yeah, maybe we have more subpolar waters or influence of subpolar waters in our area of study. But the oxygen at the same time also presents a decreased trend. And this is not correlated with this decrease in temperature and salinity. We will expect an increase, but not a decrease. So let's look at what happens with the Atlantic meridian overturning circulation. And there is this rapid slowdown until the 1990s. And this could be the reason why our oxygen is decreasing, because the lower the circulation of a water mass, the more time a water mass spends in a place, its resident time increases. And this, since the remuneration we measure, when we measure the water mass, we are observing that in terms of a decreasing oxygen. And so that could be an explanation. And from the 1990s on, we see a weakening in the subpolar gyre. And when we look at the temperature and salinity in the central water, we see that there are relatively higher values of salinity and temperature, which also could agree with this situation of having more influence of warmer and saltier water in our region of study. And again, the average value for this period is really lower compared to the previous period. And so okay, that we have influence of warmer and saltier water because they are they have fresher and cooler waters. But there is also a decrease in oxygen. And here we have two possible things. One is that are happening. One is that since the subpolar front has moved northward, there is more time, or it takes more time for the water mass to arrive to when we measure it. So the remineralization processes are affecting the water mass, even though the temperature and salinity doesn't change much. And the other reason could be that we are still in a process of a slowdown in the transport of the Antarctic medium over thermal circulation, because even though you can see a reinforcement here in the index doesn't achieve the zero, which means that the transport is not in its usual mean value. So we cannot rule out the slowdown in the transport of the Antarctic medium over thermal circulation as another reason for the oxygen change during this second period. So to sum up and conclude my presentation, I will say that we found a long-term decrease in oxygen in the Eastern North Atlantic Central Water during a 40-year period that is very similar to what is found in another coastal waters and in another welling systems. And we think that is mainly caused by two main processes. One is a decrease in oxygen in the region of formation, and a decrease in oxygen caused by the combination between the variability, the decadal variability of the subpolar gyre circulation and the slowdown of the Atlantic median over thermal circulation. And that's all. I'm happy to take any question if you have. Thank you very much.
Thank you, Paolo. Unfortunately, we don't have time for questions, so you can do the Padlet application. So our next speaker is giving us her presentation by a video. Her name is Natalia Evans, and the title is Natural Variability and Expansion of the Eastern Tropical North Pacific Ocean Deficient Zone, et cetera, et cetera.
Hello, everyone. Having me. I wish I could do this in person. However, I'm still very happy to present my work on the natural variability and expansion of the nitrogen deficit within the Eastern Tropical North Pacific Oxygen Deficient Zone. The basic layout for this talk is going to be first, background on oxygen deficient zones and why they're important, then looking at how the ODZ has varied, water direction through water masses, teleconnections with the California current system, then the expansion of the ETMP ODZ and its natural variability. Briefly, I just want to mention that I'm focusing entirely on the ETMP ODZ, this wedge here of blue off of the west coast of Mexico. It's the largest oxygen deficient zone on our planet, and processes impacting it are important because they compress habitat, create greenhouse gas emissions through nitrous oxide, as well as the loss of fixed nitrogen. Here we see projections of the volume of water that has low oxygen on the y-axis over the past and into the future. Here, so we're saying is that this model anticipates that oxygen minimum zones will expand up to around 2100, but then begin to contract again. However, ocean warming has divergent effects on ODZs. For example, stratification will lower the flux of oxygen from the surface water into the ODZ, which strengthens it. However, stratification will also lower the flux of nutrients from the ODZ into the surface waters, which lowers carbon fixation there and limits carbon flux into the ODZ, weakening it. The net impact of these processes is not well defined. On the other hand, we can look at the history of ODZs as well. Here, we're looking at nitrogen isotope low oxygen conditions. Isotopes reflect the extent of gentrification that's happened in the water column, and the sediment core record indicates the history of the strength of the ODZ. Therefore, want to look at how the ETMP ODZ itself, the water column, has varied rather than models or the sediment cores. The data I'm using for this project primarily comes from the 110 west line. Here we have 8 cruises, 7 which on this line, 1 is a little bit off. They span from 1972 to 2019, though they're more clustered in the more recent decades. There's 2 2016 cruises, a Ron Brown on 110 west, and a Colloq, which is this one east one. It's going to be marked as Colloq in the 90% data. In addition, the Pestero data source, where that core data came from, is marked here, the star. The first approach I used is similar to this paper by Horak et al. 2016. The first approach that I take is looking at the integrated connection loss along our transect here. On the y-axis, we're going to see time with past on the left and more present on the right. And then on the y-axis, we see the integrated fixed action loss. So we took our bottles that we created the data and integrated across them, looking at N star, specifically integrated. And between disk sources specified on the legend here, we have the entire ODZ between 24.75 to 27.2 here. In these points, the lines connect everything on the 110 west line. The Colloq will be an outlier not on those lines and is also systematically lower most of the plots. So you notice that the ETMP ODZ has gotten much and more intense in the past 50 years. If you want to look at how that's happened, I broke this down into specific potential density services, and we see that in the upper oxycline in red here from 24.75 to 26.2, it's only responsible for about 1/10 of the integrated fixed action loss, whereas the core ODZ from 26.2 to 26.8 and the deep ODZ from 26.8 to 7.2 responsible for most of the fixed action loss equally. The main takeaways here are that the ETMP ODZ lost about 1.3 times more fixed action loss in 2019 than 1994, which is the weakest year here. There's a similar amount of fixed action loss between the ODZ core in blue and the deep ODZ in magenta. However, our significant amount in black here is due to a combination of a significant expansion of the deep ODZ in the past 3 years from 2016 onwards, combined with an already strong core ODZ. Now, for robustness, we wanted to compare a different method for calculating the fixed action loss and see if this was just a product of our N-star integrations. For that, we have to take a brief digression through water masses. The 2 water masses that compose the ETMP ODZ. The first is the 13 degrees Celsius water mass, centered around 6.2. It's also called the upper Pacific equatorial water mass. And here's some world ocean atlas data. It's subset just for this water mass, where we see it's being formed, aka low phosphate here, attachment C, and then it moves out, and you can see the highest phosphate occurs in both these ODZs here. We also have the northern equatorial Pacific intermediate water, or the NEPAW, set around 6.8. It's also called the deeper Pacific equatorial water. It's formed by mixing of the Pacific deep water and the Antarctic intermediate water, and its lowest oxygen is up here in the ODZ, where it's the highest phosphate. Now, why this is important is that I can subset these water masses out of the World Ocean Atlas data, and I can look at, as they move, how their nitrate to phosphate ratios change. For example, in this process, we can see approximately where they switch from the 16:1 aerobic respiration to anaerobic processes, where we increase phosphate but decrease nitrate. So the reason why this is important is basically for the strength of the ODZ, the second method, I'm basically just calculating how far along this vector points are from this reference 16:1 line here. The slope is negative 62:1. Now, if we return back to our initial data, I'm adding this plot here. And this is once again looking at that strength of the ODZ, how far those points are across that line, and basically the top 10 values for each cruise. And here we see that the trends are quite similar. Once again, the core ODZ was higher and it got a little bit weaker and then it got stronger. We have a dip here in 2016 we didn't see kind of integrated, and then a return to strength in 2019. The deep ODZ is also quite similar. It's a very low change until we hit about 2016, and then it jumps up. However, this method allows me to calculate the stoichiometry, the concentration of nitrogen that changed. So that's 2.4 micromole per kilogram of nitrogen, which is a 1.3 increase in this core ODZ from 2012 versus 1994, which matches the data we have here as well, which suggests that both these methods are pretty good. In addition, I can also look at the station action loss, which I calculated at the strength of that vector, on contour maps here. So we have here is on each of these is basically a snapshot through the ODZ. We have the cross section from Baja on the right side of each plot to 14 degrees north. We have potential density on the y-axis. We have shallow up here and deep down here. And the colors represents the magnitude of nitrogen versus phosphate. So a larger value means that there is less nitrogen in the water column. We see here is I also use a cutoff of 8 arbitrarily just to look at sort of the size of each of these. One of the first things we see is that in 1994, it's the weakest ODZ. It's about 1400 AD. There's noticeable shoaling of the ODZ, which in strengthening would happen in 2012 with that core ODZ. And then if we're thinking about the rapid deep ODZ expansion, that's occurred primarily just through deepening of this ODZ. And I don't know the cause of this expansion, and it's definitely worth more research. With that, I also like to point out that this ETMP ODZ is very closely connected to the California current system. For example, the California current system is fed by these Pacific agricultural waters off the ODZ via the undercurrent here. So the same water masses in the ETMP ODZ feed up all the way up to Alaska with this method. If you look at the strength of the core ODZ here, see that it matches very nicely with the mean oxygen sampled on the CalCoffee program. So here I just took the oxygen concentrations from 100 meters to 400 meters and averaged them all together. That's what our trend here is. You note that it is quite closely correlated with the strength of ODZ. For example, in 1994, we have a weak core ODZ, so not much phase action has been lost. We have a high amount of oxygen. In 2012, our ODZ is stronger. We have less oxygen. And then we see a little bit of a lag here before it starts to go oxygen. So we're probably entering another period of deoxygenation at this point. And so my previous work, I determined that the deep Pacific agricultural water, or the NAPW, is responsible for 80% of the deoxygenation in the California current system. You can look at that more in detail if you want to. However, I'd like to focus on a much more interesting aspect of this project, which is the natural variability of the ETMP ODZ. Once again, I'm going to return to this core ODZ strength, but this time I'm going to compare it against the nitrogen isotope data from Deutsch et al. 2014, which is replotted here. So we see that these correlate well. In 2012, we have a strong ODZ, we have strong isotope fractionation, 1994 is weaker, and then correlates back here. Now the cool thing here is that Colloq and Timms in 2016 published a 1,200-year-long record of this sedimentary nitrogen isotopes all through here. Now what I can do is I can just drop my little 4 points from 1972 to 2012 on top of this record here. Then I can derive some sort of conversion factor from the isotopes to the maximum phase action loss here. I can fit these, find a slope and an intercept. And that's shown here is basically converting the Pacific core data and then versus the arrangeable in blue. However, I can extrapolate that fit across the entire sedimentary nitrogen isotope record, which granted it's only 4 points, so it's not the best fit, but it's currently what we have. And with that, I can get a distribution of the values for the maximum phase action loss that has occurred over the past 1,200 years. We see that in this plot here, we have the strength of the ODZ, that top 10% measure phase action loss. The points are the time series that we saw here, and they're only vertical just so you can read the numbers here. And then in the light blue, we see a histogram. This is the distribution of the ODZ strength based on that conversion factor here. You notice it's quite normal, which is fantastic. However, it allows me to calculate confidence intervals. I chose a 99% confidence interval. That's what the IPCC uses for a virtually certain climate change. And you'll notice that with this 99% confidence interval, it exceeds the variability we've seen in the past 50 years of the core ETMP ODZ. So therefore, we cannot say that anthropogenic impacts have caused this variation yet. We don't have enough, small enough confidence interval yet based on the 4 points extrapolation that I made. I can also convert this into the water column. So we have our magenta confidence interval here, but this is sort of hard for somebody if they're going to be using in the future. You have to do this conversions from successional loss to nitrogen to their samples. Instead, I put this on a nitrogen phosphate plot here. So basically, if our samples, the top 10%, exceed either of these bounds, we can be virtually certain that it's because of climate change. So the conclusions of my talk are that we do see a 1.3 times stronger core in the ODZ between 1994 and 2019, both in the integrated data and the maximum. We cannot yet claim climate change has caused this intensification, but we do have cost intervals. 9.2 to 12.5 micromole per kilogram of fashion loss. That's what we have so far. I encourage to try to fine tune this, but it's a good first pass. However, that's looking only at the core ODZ. There's this recent increase in the ODZ strength in the deep ODZ from 2016 on, caused by expansion and this deepening that I'm not sure what's causing it. It's quite important. With that, I'd like to acknowledge everybody who helped with these 8 cruises. Caitlin Timms, Will Barrelson, and other researchers for collecting and sharing all the sediment core records. Of course, everybody who kept the CalCAVE program running, which I compare against. Isaac Schroeder specifically collated and shared the data that updated this we saw here. Johannes Karsten and Matthias Tomzak developed the optimal multi-parameter analysis package I use for water mass analysis. The USC Riley Fellowship funded Joanna Dakota, and NSF, of course, for funding all of this work that we all did here. I'd also like to mention that if you're interested in this, the water mass analysis with World Ocean Atlas data is currently in review at Limnology and Oceanography, but it's also, there's a previous draft of what is a preprint. And while the ETMP ODZ time series, the bulk of the data I showed you, is currently going to be resubmitted tomorrow, all of the data, as well as the code to generate and process that data, is available on Zenodo. You can look that up. It's all there if you're interested. With that, I cannot be here in person, unfortunately, but if you have any questions, please feel free. ncevans@uc.edu. I'm happy to take any questions, any feedback, and if you wanted to like Zoom, anything like that. I'm also hoping to graduate next year and starting to think about a postdoc. So if that's an option that you're interested in, I would love to follow up with you about that as well. Thank you so much.
Thank you, Natalia. And let's move right on to the next presentation, which is by Hernan Garcia. Hi, Hernan.
Hi.
Go for it.
Okay. So I would like to talk a little bit about the estimates of O2 content variability and trends from the 65 to 2019. And I would like to acknowledge all my co-authors here. I don't seem to be able to, okay. I'm sorry. Okay, so the outline is, first I would like to tell you a little bit about the next generation of the World Ocean Atlas. We use a blended mixture of Winkler and sensor-based data, and the data is coming from the World Ocean database. And then I would like to show a few of this global content variability and CTD data. So for those of you who may not be familiar with the World Ocean database, WD is the world's largest common format open access database of profile oceanographic data from 1772 to present. Currently has almost 18 million profiles, And WD is an IOC-IOD project, an international effort for and by all countries, and is FAIR compliant. So we take a great deal of global data common in many, many, many different formats, and we put them into a uniform digital format and provide open and access to that data. And that data is used for generating multiple products worldwide. So just looking at the oxygen data available in the World Ocean Database, right now we have almost 2 million profiles of oxygen, and most of those are after the 920. The volume of now of sensor-based oxygen data has surpassed all the historical Winkler data that we have ever collected. So the sensor-based data has revolutionized and provided an unprecedented spatial and temporal coverage. So this is an idea to show a glimpse that even though we have a great deal of data, there is no complete coverage of the ocean. So these are the Winkler, the Argo, CTD, and Glider data, which are the largest numbers in the graph that I showed before. So we do not have complete coverage. Glider data, for example, which is prolific in the number of profiles, is for now is limited to the coastal regions, for example. The data that we derive from the World Ocean Database is used in the construction of the World Ocean Atlas. And we have Ocean Atlas for oxygen from 1994 to 2018. And it has always been a dream of mine to create the next generation of World Ocean Atlas for oxygen using sensor-based data. It's just that before we didn't have the quantity and the quality to do that. So now we do. So in the next Atlas, which will be released in 2023, it will be a blended climatology using Winkler, CTD, Argo, and maybe Glider data. Okay, so this is the roadmap that our group is using to look at variability. So we get data from the World Ocean Database, and we QC, quality control the data for bottle, CTD, and Argo. Not all the data are created equal or the same quality, so we have limited our analysis for 1965 for bottle data and CTD after 1987 and Argo data after 2002. With this, we first create a basic baseline climatology, which contains the climatological mean, seasonal, and monthly over 1 degree all over the ocean at 102 depth levels, covering between the surface and the bottom, essentially. And then based on this climatology, then we create these season anomalies based on pentale composite periods covering the entire period from 1965 to 2019. And from those anomalies, then we can integrate and look at the variability over time. We can look at, of course, global and coastal, hemispheric, and so on and so forth. So that's what I would like to show you next. But before we do that, it's important to note the importance of quality control. We cannot just put data into a climatology and expect the results to be enough to resolve climate signals. So on the left side, we have the climatology based on bottle oxygen. In the middle, we have the bottle plus CTD. and then at the bottom, the bottle, CTD, and Argo. And if you look at those by eye, those climatologies, arbitrarily chosen at 325 meters, you can see that there is very little difference. But when you compare them to a reference, let's say the World Ocean Atlas 2019, on the top is the difference between the bottle plus CTD minus the Winkler. And you can see that there is still a few regions where there is a very large changes. This changes are more than 10 micromoles. At the bottom is the bottle CTD plus Argo minus the Winkler climatology. And there's still a substantial amount of Argo profiles that seem to underestimate the signal. So those need to be quality control and flagged. So here I am only showing you the analysis, the Pentillo analysis from 1965 to present using only bottle and CTD, because I'm still working on the Argo data. So on the far left, you will see the global trend for different depth layers between the surface and 500 meters, surface and 1,000 meters, and 0 to 2,000 meters. And you can see that in all layers show a decrease over time, deoxygenation, if you will. The global trend for the entire 0 to 2,000 meters is about 840 thermoles. Then if you divide that into the northern hemisphere and the southern hemisphere variability on the far right, you can divide it into different latitudinal bands, you can see that all bands and in both hemispheres show a decrease in oxygen. So that seems to be fairly consistent, except that the decadal scale variability in the northern hemisphere seems to be larger than the one in the southern hemisphere. That also might be real, or it might be an artifact of that we have a great deal of more data in the northern hemisphere than in the south. I'm still working on that. Okay, so some preliminary things, some reality checks here is that if we start with the same data and we apply different methods to look at the variability, we come up with comparable results. So that is very good news that the analyses provide the same similar results. That means that the data is not the issue over the methods. The other issue that we were very concerned is about the lack of spatial and temporal data coverage. So in some exercises to sampling O2 models where there is Wilson database data, and then try to apply a mapping technique to that, it seems like the mapping underestimates the full model data, because presumably there is a great deal of smoothing. But the differences are not super large. So, but we're still trying to quantify that. And the third thing that we are concerned about is,
5 minutes.
Okay, is that trying to resolve the uncertainty in the results. Okay, I think that the main part that is of interest is that we need to understand what is the attribution of the variability and the uncertainties of that variability. Getting consistent high precision measurements in the ocean, especially in low oxygen areas, is difficult, even by Winkler methods. The coverage, the coverage of Argo data, even though it is unprecedented in area-wise, they don't normally go as deep as the oxygen minimum zones because they go deeper than 2,000 meters. So I would love to encourage everybody to consider sharing oxygen and other data, because that's how we all scientists are able to construct and benefit from the data and create this work. On the graph, I'm showing a little bit about the mean oxygen anomaly variability between 1965 and present. And you can see that there is a great deal of deep variability, not just the surface, to up to 2,000 meters. And on the bottom is the standard deviation of that anomaly. And you can see that there is a great deal of heaving of those isograms and the different points in time where that strength in stratification for oxygen is large. Okay, so in summary, in 2023, the World Atlas will include a blended climatology, and that will be able to resolve annual, seasonal, and monthly fields, 102 depth levels to 5,500 meters, 1 degree, and it will contain quality control, bottle CTD, argon, and hopefully glider data. And then I also show that our preliminary analysis indicates that a global oxygen degree of about 1 to 2% is estimated between 0 and 2,000 meters. We are working now on adding quality control Argo data and extend the analysis to 2021. Thank you so much.
Thank you, Hernan. We have time for one short question.
Thanks, Hernan. Question about the 1 to 0 to 1,000 meter depth range. Your Taka Ito earlier in the session, I think his co-author here, he had an estimate that was about 70 or 80% higher than yours here, and you gave a 10% error range. Is that due to the different methods, or are these not accounted in the error range, or is it different data sets that you both use? Didn't understand that.
I think that, well, there's still a little bit of work to validate this, to have some internal consistency in the results. So model results and observations are a little bit different. And so
observation estimates and using the same World Ocean Atlas data, as far as I know.
Yes. Well, I don't have an answer for that. Let's put it that way.
Okay, thank you. Thank you very much. And our last speaker today is Ariel Petzner, and she is going to speak about global coral reefs will experience moderate to severe hypoxia before the end of the century.
Everyone hear me? Great. Okay. Well, thank you for having me. I will try to make sure we all get to the brewery on time today. My talk is going to be a little bit different than some of the rest of the talks in this session, but I think that it follows pretty nicely from some of the stuff we heard on Monday. So traditionally, coral reefs are assumed to be well-oxygenated systems. They have these crystal clear waters and a high abundance of primary producers that we would expect to be producing, lots and lots of oxygen, especially during the daytime. However, as Professor Altieri has shown, as well as some other people who have presented in this conference so far, that hypoxic events can occur on coral reefs, and they lead to both sublethal and lethal impacts on reefs, such as movements of these invertebrates towards the surface, as well as bleaching and mortality of the corals themselves. And so on a global scale, coral reefs are experiencing declines in coral cover. This figure is from a recent Status of the Corals of the World report showing these declines in the hard coral cover of the last few decades. And while a lot of this can, of course, be attributed to changes in temperature, which lead to bleaching and mortality, especially during El Nino years, as marked on the plot, there's also a lot of other drivers and stressors that are affecting coral reef hard cover. One being, of course, increasing nutrients, which leads to overgrowth of algae, perhaps increase in CO2 and ocean acidification, which may have consequences for calcifying organisms like corals. However, the role of oxygen has not been super well resolved, especially on tropical coral reefs. And so from Andrew's work, we know that we're probably very likely underestimating the occurrence of hypoxia on tropical coral reefs. He showed this figure from his 2017 paper, which I've used a lot as a basis for some of my research. But again, you can see this overlap in the documented dead zones and in the purple areas, which is where we can find coral reefs around the world. And given this overlap, we would expect to find probably a lot more of these events. However, these yellow dots, demonstrate back in 2017, at least, places where we knew mortality had been driven by hypoxia. And so it's pretty likely that there's probably a lot more of these events happening that we just haven't been looking for. And so to kind of try to address some of these gaps in our knowledge, I've been working on compiling a global coral reef oxygen data set. And so this data set includes 34 or 33 reef sites at 12 different locations around the globe. So the map in the middle shows these 12 different locations and there's satellite images going around the border of each of these locations. And then there's also multiple sites at some of these locations from different deployments. And so a lot of these data came from our lab, from a lot of our deployments over the years, and also the many collaborators that are involved in this project. And the idea was to try to get as many oxygen data sets as we could to kind of establish what oxygen looks like on these reefs. And we tried to get a representative data set. So most of these data were collected by CFOX sensors, which use Ondera oxygen optodes to measure oxygen. We had a lot of different types of reef sites. So the depths of these deployments ranged from 0.5 meters down to 17 meters at some of the deepest sites. There was a range, of course, in the number of days that these deployments lasted, but they're mostly collected between 2015 and 2019. And I think most importantly included a variety of coral habitats. So we had kind of traditional fringing reefs, as well as deeper reefs, pore reefs, lagoons, and also reefs that are dominated by primary producers like seagrasses. And so the main motivating questions for my project was looking at how does baseline oxygen differ between different sites around the world? So what does oxygen even look like on these coral reefs? Is it the same everywhere or is it different? How frequently do global coral reefs experience hypoxia under present day conditions, looking at our present day data, and then also trying to calculate how hypoxic event intensity, duration, and severity will change under projected warming. And so before I get into some of the data, I wanted to go over something that has been brought up, I think, multiple times in our talk so far. But the thresholds of hypoxia can vary widely between different taxa. This is from a meta-analysis in 2008 of mostly temperate species, because that's where a lot of the data is, looking at median lethal and also sublethal thresholds of oxygen for different taxa groups. And you can see that there's a wide variety depending on which group we look at, and also whether we're considering lethal or even sublethal thresholds. And of course, traditionally, we've been using this 2 milligram per liter threshold to denote what severe hypoxia is, which is about 61 micromoles per kilogram. And while this may capture a lot of our lethal thresholds, I would argue that these sublethal thresholds are also important and will have consequences for ecosystems. And so in the study, they found that 90% of these experiments reported median sublethal oxygen concentrations of less than 5. And so for the study, I actually employed 4 different potential thresholds of oxygen that may be relevant to different species on these reefs, ranging from severe to moderate to mild to weak, with the 5 milligrams per liter or 153 micromoles per kilogram being the kind of upper limit. And so looking at some of the data from these different reef sites, we found that the mean and extreme dissolved oxygen conditions varied widely among reef habitats and also between sites at the same location. So this figure didn't show up quite correctly, but these are histograms of dissolved oxygen concentration and dissolved oxygen saturation for each of our 12 locations, with some of the ones that have multiple sites plotted on top of each other. And you can see, for example, if we look at a place like Dongsha Atoll, which is in the South China Sea, and is a mix of patch reefs and also reefs dominated by seagrasses, there's a wide range in oxygen conditions that are experienced at these reefs, from extremely low oxygen concentrations and hypoxia to extreme supersaturation. But if we compare to a different reef like Tutuila, which is a very deep pore reef that slopes down the side of the island, the oxygen concentrations experienced there are much more modulated and much higher on average. This is supposed to be a plot of a climatology, but it didn't show up, unfortunately. But we could see from this plot that we would see these typical diel cycles between hours of the day where we had low oxygen in the early morning and high oxygen in the late afternoon. However, the amplitude of these climatologies are very different between these different sites around the world, which kind of establishes that each of these reefs have very different environmental histories. And so they're experiencing these very different oxygen conditions, even under present day conditions, which again, I think lends to the fact that maybe these one singular threshold may not be relevant for all of these reefs around the world. And so using some of this data, we also leveraged location-specific temperature rise predictions from the CMIP6 models, using these 4 SSP scenarios to make predictions of what temperature would look like under these different scenarios for each of our 12 locations by the year 2100. And we also included a 6-degree kind of extreme heat wave scenario as like an acute event that could occur on these reefs. And using this projection in temperature, we then calculated what the decrease in oxygen solubility would look like on each of these reef sites, as well as what the increase in reef respiration would be using a GO2NE relationship. And so from this data, we found that warming will reduce the available oxygen on reefs, leading to increased exposure to hypoxic conditions. So this figure shows dissolved oxygen concentration. The darker shaded boxes is the mean range, and the lighter shaded boxes in the back represent the kind of extreme ranges found in blue at present day at each of these sites, and then under these increasingly warming scenarios in the warming colors. And again, we have our 4 thresholds denoted here in dotted lines. And so regardless of which one site that you look at, under increasingly warm scenarios, we would see the amount of oxygen available on these reefs to decline with warming. However, places like Hog Reef, for example, which is in Bermuda, which is a pretty far north reef that has naturally very high oxygen concentrations under present day, even under the most extreme 6-degree heat wave scenario, wouldn't even really experience any hypoxia at all, given the thresholds that we're using. However, a place like Dongsha Atoll, which already has hypoxic conditions under present day, would actually experience some level of hypoxia almost all of the time under a 6-degree heat wave scenario. And so altogether, we found that at present day, 84% of the reefs that we surveyed experience weak to moderate hypoxia, at least at some point in the deployments that we have, and that 13% of the reefs that we found already experience severe hypoxia today. And this would increase to nearly all of these reefs experiencing weak to moderate hypoxia under the SSP 5-8.5 scenario, and nearly a third of these reefs experiencing severe hypoxia under that same scenario. And so we also found that warming will increase the duration of hypoxia across many of these reefs. So we identified hypoxic events and then modeled how they would change under these different warming scenarios. And this figure is showing the percent of sites that experience these hypoxic events of different durations, ranging from less than an hour to greater than 24 hours under our 4 different thresholds. And regardless of the threshold that you look at, we see this shift towards long duration events under warming for each of our thresholds. And I think that this is important because not only is the level of oxygen important, biologically, but it's also how long are these systems being exposed to this. So it's a combination of not only the intensity, but also the duration. And from this meta-analysis, we can see that the median lethal time varies by orders of magnitude, depending on which species groups we look at. And so we also looked at kind of cumulative duration and intensity and the severity of hypoxic events. And regardless of the threshold that we look at, we see that the total duration, total intensity, as well as the severity, which is kind of a measure of duration and intensity, will increase under our different warming conditions for each of our reefs. And so in summary, we found that present day mean extremes of oxygen widely among and within regions. This is our climatology plot again. And hypoxic conditions are pervasive around the world under present day conditions. So it's probably pretty likely that we're missing a lot of these events that we haven't, been historically looking for. And that warming will increase the duration, intensity, and severity of hypoxic events moving into the future, regardless of which thresholds are relevant to these species. And so what does this really mean for reefs and what does it mean for them, on a larger scale? Well, unfortunately, the thresholds of hypoxia are not well resolved for reef organisms. From a 2020 review, these blue highlighted species were the species that we have about tropical coral reef species. And you can see that even within the small amount of data we have, there's a lot of variability in both sublethal and lethal thresholds. And I think some of the presenters from Monday are also looking into testing this on more coral species, but we really don't have the data to understand which thresholds are going to be relevant for not only corals, but also all the other species that are found on tropical reefs. And even in terms of thresholds, we don't really know anything about the duration, the frequency of these events, or the recovery time between events, and how that will lead into their tolerance for low oxygen. And of course, as we've talked about in this meeting as well, warming and hypoxia are not occurring in isolation. Acidification and hypoxia tend to co-occur because a lot of the same drivers lead to these events, and they can be additive. And we also know that warming increases the sensitivity to low oxygen for many species, changing their P-crit value. And so altogether, I think that this may have severe consequences for reefs and reef-associated taxa. And I think many of these things have been mentioned already in this meeting, but continuing long-term monitoring of reef dissolved oxygen, because there's just not a lot of data sets out there, and having somewhere to report it that's very central and can be QA'd and QC'd would be really important. Determining relevant oxygen thresholds for reef organisms, both lethal and sublethal, because I think, if we're just looking for mortality, it may be too late if we're only looking for that. And then also considering the duration, intensity, and frequency of the events, not just the intensity. And then also, I think, understanding the role of environmental history in determining oxygen thresholds. And that's what some of my other PhD research has been about, looking at corals that grow in these naturally very variable ecosystems. So I just want to highlight that this was a super collaborative effort and required the data from many, many labs over many, many years. And I would be happy to take any questions.
Marie-Laure, do we have time for a question? Marie-Laure, do we have time? One question. Yes.
Thank you for your presentation. I had a small question. I wanted to know, like you showed your study sites are all over the globe, and I wanted to know, how do you compensate when you come to comparate between the different data? How do you compensate the spatial heterogeneity? Because I imagine in each site you have different conditions. So how do you compensate this spatial heterogeneity?
Yeah, it's a great question. I mean, there's nothing really in the calculation specifically that compensates for it. I mean, the respiration rates for each of these sites are calculated individually based on the data for that site. But I think the goal of this project really was to embrace that heterogeneity and get, representative reefs from very different systems, and not just look at, one type of reef, and to kind of get that diversity included in the data set.
Okay, well, I'd like to thank all of the speakers for doing a really nice job.